Hey, it's Juan Tutors, and today we are working on the January 2025 Chemistry Regents, the last Regents that I have to record of the January Regents, so I'm pretty excited about it. And it's one of the very last Chemistry Regents that we're ever going to take. We are changing standards next year, so if you're taking the Regents in the 2025-2026 school year, you may be taking this Regents or you may be taking a modification of this one. They're both going to be offered at different times of the year. So that said, we are going to basically jump right into the Chemistry Regents. The first 50 questions are multiple choice questions, and they do depend on your knowledge of chemistry, but also your ability to use a reference table. The living in the Earth Science Regents is the Regents that is the most dependent on the reference table. The second most dependent on the reference table is physics, which is a very formula based class. And then this one uses the reference table much less than the other two Regents that I just mentioned. And then, of course, there's the living environment Regents, which doesn't even have a reference table. Okay? So that said, we're going to jump right into number one. And I just want to say, I believe in you. I know you could do it. I know you could do the best that you can if you do the work. One of the things that you could do for yourself is just watch this whole video and make sure that for every single question that I ask, try to come up with an answer for yourself, because what that'll do is it'll test your knowledge and it'll help you correct the pieces of information that you don't know. If you don't do that, then you're just listening and you're just kind of hoping that things osmose into your brain. But if you actually choose an answer for every single question, you will do a lot better just by choosing. Even if you're wrong, just by choosing an answer, you will do a lot better on the Regents that's coming up. That said, number one, the subatomic particles in the nucleus of an oxygen atom include electrons only, neutrons only, protons and neutrons, or protons and electrons. And it's important to know that the way the nucleus kind of works, you got a bunch of protons and a bunch of neutrons in the nucleus. And these are nucleons. And I'm drawing them all the same color, but you could draw them different colors if it, makes it make more sense to you. But protons and neutrons, and then you have electrons in kind of a cloud, but we often draw them in circular shells. Okay? And then the oxygen has, I believe, six electrons in its most outer shell and two more electrons further in, for a total of 8 electrons in orbitals, and it's got 8 protons in the nucleus, and then it's some number of neutrons. Usually, in fact, 8. That's just for oxygen. So the point is that the nucleons are particles in the nucleus, the larger particle in the nucleus, and they are protons and neutrons. You may have learned, or if not now, but if not, you'll learn in physics that protons and neutrons are actually themselves composed of smaller particles called quarks. So yes, there are smaller particles than just protons and neutrons. There are quarks, but the nucleons are the protons and the neutrons, which gives us the answer of choice 3. Okay, electrons are they orbit the nucleus in the shells. Okay. Number 2, which phrase describes the charges and number of protons and electrons in an atom? Do they have opposite charges and are equal in number, or opposite charges and are unequal in number, or have the same charge and are equal in number, or have the same charge and are unequal in number? And this is what I call a 2x2 question. So what is a 2x2 question? A 2x2 question is a multiple choice question where the choices, instead of just looking at it as 4 choices, you could actually look at it as 2 sets of 2 choices, either opposite or the same. Okay, make that one wiggly, make this one a little more wiggly. And then separately, are they equal or are they unequal? Okay, so, and you can make those choices separately. If you try to think about both choices simultaneously, you can be convinced that that's actually the goal, and it's not actually, that's not the goal of these 2x2 questions. They actually want you to answer for each individually. Each one can be determined individually, which is correct. And in fact, this is talking about protons and electrons. Protons and electrons. The word proton comes from pro, meaning positive. The prefix of proton comes from pro, which is positive. And then electrons have a negative charge. Okay? So they do have opposite charges. So any of the answers that are incorrect, that say same charges, are incorrect. And so we could cross out choice 3 and choice 4, and now we have a passing problem. What is a passing problem? I'll talk about it later. Then the question is, are they equal in number or unequal in number? So in an atom, the number of protons is equal to the number of electrons. And in an ion, the number of protons is not equal to the number of electrons. Okay? So that means that since this is an atom, we are looking for an equal number of protons and electrons. Number 3, in the wave mechanical model, which term identifies a region in an atom of lithium that is the most probable location of electrons in the ground state? Is it a hard sphere, polar bond, orbital, or spectrum? Some of these answers sound scientific, and so we may lean towards them, but it's important to know what the meaning of these words are. So first, this is the hard sphere model. This is a very old model, and it's not correct. So is it? Are the electrons located in polar bonds? Polar bonds do have, electrons in them, but that's not the only place where the electrons are found. So this causes a bond between, or this is a bond between two atoms. Okay? Or ions. Two atoms, two atoms. So that's not it. So now what about orbital versus spectrum? Spectrum is probably the second most common, or the most common incorrect answer. The spectrum has to do with the emissions or absorptions of photons of specific wavelengths. In an atom, in an ion, in a compound, in a mystery mixture, like a star, or when you do physics, or just another type of sample. But this has to do with the emission or absorption of those photons, not the actual electrons themselves, not their location. So the location of the electrons are called orbitals. Okay, orbitals. Number 4, an atom of C12, carbon 12 in the ground state, and an atom of carbon 13 in the ground state are defined as isotopes of carbon because these atoms have the same number of protons and the same number of neutrons, same number of electron shells, different number of neutrons, or different number of electron shells. And so we need to think about which of these, some of these statements are just actually false. So for example, they don't have different numbers of electron shells. They have identical electron shells. Okay. then do they have, so that there's a hint also that choice 1 or choice 3 might be the answer, because choice 1 and choice 3 are opposites. So yes, it's true that choice 2 and choice 4 are also opposites, and this is technically true, this is true, but this is not why they're isotopes. And there are other atoms that have the same number of shells. Carbon has 2 shells, so does oxygen. Just the location and the number of electrons in those shells is different. So this is not correct. Then this one, the same number of neutrons or different number of neutrons, that's actually what changes the mass of the carbon. Carbon 12 has, according to the reference table, 6 protons rather, and 12 minus 6, which is 6 neutrons. And carbon 13 has the same 6 protons and 13 minus 6, which is equal to 7 neutrons. So they definitely have a different number of neutrons, okay? Number 5, at STP, which property can be used to differentiate between a 2.0 gram sample of oxygen, O2, gas, and a 2.0 gram sample of helium gas? Is it mass, temperature, reaction with sodium, or phase of each sample? Now, many of these, because this is an earlier problem in the test, many of these can be eliminated just from the context of the problem. It turns out that there are other features of the sample that can be used to eliminate, to identify one versus another, but there are some that aren't listed in this list. Okay, so it does say, so we got to differentiate between a 2.0 gram sample of oxygen and a 2.0 gram sample of helium. So what can we use to differentiate? Remember, differentiate. The mass is the same. Now I'm going to cross it out. What about the temperature? STP here stands for standard temperature and pressure, which is 1 atmosphere, or 101.3 kilopascals. And also the temperature is 0 degrees Celsius, or 273 Kelvin. 273.15 Kelvin, 273 Kelvin. So because the sample's at STP, the temperature is the same. Okay, what about this one, the phase of each sample? It actually does say that the sample is in the gaseous state. So they didn't have to do that. Why didn't they have to do that? Because they said that it's at STP. And in your knowledge of chemistry, hopefully you know that helium is a gas. In fact, helium stays a gas for a while. You have to lower the temperature of helium tremendously to get a liquid helium. And oxygen actually also stays gas for a very long time as you lower the temperature. So the but that said, and also of course we're breathing in oxygen all the time. There's gaseous oxygen in the atmosphere all the time. So at STP, oxygen and helium are both gaseous, but they told us that in these 2 letters, so it's not that one. Therefore, the reaction with sodium does make sense. And even if we didn't know how to eliminate all the other ones, the reaction with sodium is one that we could have guessed at, because helium is a noble gas. Which means it does not react very easily at all. And in fact, you have to go really, really specialized to even find a compound that has helium in it. It's really rare. Noble gases really, really barely react. and helium much less than any of the other noble gases. I mean, it doesn't. If you put it with sodium and try to do a lot of things to it at STP, you're not gonna see a reaction. Okay. Number 6, how do the molecular structures and properties of oxygen, O2, and ozone, O3, compare? Choice 1, they have different molecular structures and the same properties. Choice 2, they have different molecular structures and different properties. Choice 3, they have the same molecular structure and the same properties. And choice 4, they have the same molecular structure and different properties. O2 and O3. So what are O2 and O3? O2 is the oxygen that we basically breathe in the air. So that's the primary version of oxygen that you'll find in our atmosphere. One big exception is ozone. Do you find ozone at the level where we are, ground level troposphere? Not unless something frustrating is happening. Like, for example, pollution is able to create ozone at the level, at ground level. I mean, it is a chemical. You could produce ozone through chemical reactions, right? Another way that ozone is produced is through electrical shorts in your walls. So if you're ever wondering what ozone smells like, now I'm starting to actually think that electrical shorts were actually a lot more common when I was a kid, because my teacher would say the smell that you get when you have an electrical short, and everyone would be like, "Oh yeah, I know that smell." I'm trying to think of a single time where I've mentioned an electrical short other than when I was a kid, that as people actually know what that smells like. But there is a smell. So if you smell like an electrical smell, what that smells like, I can't describe it to you. But if you're anywhere where you see a lot of sparks and there happens to be a smell, that smell is ozone. Okay, usually. So that said, O2 and O3 are different. O2 has a structure that looks like this: an oxygen and an oxygen bound together. This is oxygen, and then O3, ozone, looks like essentially like this. Okay, and now you're wondering, like, this doesn't seem to fit the usual models of electron shells that we're accustomed to seeing. And you are absolutely right about that. So the thing is, and I think more accurately, if I drew it this way, you're right. This doesn't fit the usual models that you're used to seeing. The thing is, ozone is not a very stable molecule. It does react relatively easily with other things. So we don't have much ozone in the atmosphere. In fact, that's why the hole in the ozone that you've heard of is such a dangerous thing, because it's not like we have a tremendous amount of ozone up there. And what ends up happening, the reason that the hole in the ozone appears is that there happens to be some chemicals up there, including chlorofluorocarbons, that catalyze the breakdown of ozone. So it takes a certain amount of energy to break down ozone. Ozone is more likely to be broken down than to form in the atmosphere. And by lowering the activation energy required to catalyze ozone down to O2 and another chlorine-based chemical, you need very little catalyst. So that's the danger of releasing chlorofluorocarbons. That said, we just established that the structure of ozone and the structure of oxygen, O2, are different. So they do have different molecular structures. They do not have the same molecular structure, so we could cross out choice 2 and choice 3. And now we've also talked about some of the properties that they have, and they do also have different properties. Oxygen, for example, lets UV rays pass through it readily, whereas ozone actually absorbs UV rays. So that's just one great example. So they have different properties. Number 7, which substance can be broken down by chemical means? Is it aluminum, ammonia, argon, or arsenic? And so we can't break down a substance via non-chemical means unless it is a compound. So chemical means can break down compounds, but not atoms. And in fact, 3 of these are atoms. Aluminum is Al. Argon is Ar. Arsenic is As. And you could look these up in the physics reference table, whereas ammonia is actually NH3. NH3. So the only one that is a molecule and can therefore be broken down through chemical means is the ammonia. Number 8, which type of bonding is present in a sample of zinc at STP? Is it covalent bonding, hydrogen bonding, ionic bonding, or metallic bonding? And we do want to know what kind of bonds these are. Covalent bonds means, keeping in mind, we do have to know what zinc is. And this is a metal. Okay? Now, what is a covalent bond? In a covalent bond, 2 atoms share 2 electrons. In a hydrogen bond is interesting. That occurs, it's a very strong attraction between the hydrogen and the oxygen in a molecule of H2O, of water. Why am I giving it in this example? Because water is the one big chemical that you want to know has hydrogen bonding. Hydrogen bonding is special. It's more than just an attraction. It is semi-stable. So it's semi-stable meaning that when the attraction occurs, the attraction can actually last longer than just the molecules get close to each other. It has to, once the hydrogen bond occurs, it has to get broken down through kinetic energy interactions, collisions with other atoms or molecules in the water sample. So it's a small enough bond that it is constantly, they're constantly being broken down and reformed, and broken down and being reformed. In fact, there's more that are broken down and reformed than there are, for example, the covalent bonds between the hydrogen and the water in a single H2O molecule. But do think of it as an extremely strong attraction between the hydrogen, which is positive in the H2O, and the oxygen, which is negative in the H2O. There are other molecules that have hydrogen bonds, and I think we will talk about at least one later, if I recall. But the big one to remember is for water. Now, what is ionic bonding? Ionic bonding is when one ion, one atom or molecule, for all intents and purposes, let's say it that way, steals one or more electrons from another atom or molecule. Okay? And what happens after that? Wow, that's barely legible. Molecule. And then those ions when they gain or lose an electron, now they're called ions, and then those ions bond to each other. Notice in that case, the ions bond to each other because they now have an extremely strong attraction to each other, because one of them has a strictly positive charge and the other one has a strictly negative charge, and that attraction is extremely strong. And whereas metallic bonding, what is metallic bonding? Metallic bonding, I think, is one of the coolest bondings that exist. So the electrons exist in a sea of free-floating electrons. In the substance. So in zinc being a metal, its bonds are metallic. Number 9, which formula represents a non-polar molecule? CH4, HCl, H2O, or NH3? So what is a polar molecule and what is a non-polar molecule? A polar molecule is one in which the charge is shared unevenly between two atoms in the substance, or two sides of the molecule in the substance, so that one side of the molecule turns out to be more positive and the other side of the molecule turns out to be more negative. The side that more strongly attracts the electrons ends up being more negative, and the side that less strongly attracts the electrons is more positive. And then, of course, there's ionic bonding, where the sharing is completely unequal because one of the things steals the electron from the other. So CH4, C is bonded to 4 hydrogens. This is called methane, and it's actually very nice and symmetric. It's got a tetrahedral structure. Like that, and like 3 down and 1 up, 3 down and 1, like a tripod and 1 up. It's really very nice and nonpolar. HCl, though, the hydrogen gets attracted to the Cl, and then the Cl essentially steals that electron, and so we have a positive side and a negative side. Okay, the H2O looks like this. It's a bent molecule, and the 2 bars are a bond, so they represent 2 electrons. So you have a positive side and a positive side, and then you have 2 sets of electrons here, so you have a negative side here. And this is the source of that very strong hydrogen bond between water molecules. So this is polar. This is polar. And NH3 has a similar, I can't say a totally similar structure as water, because NH3 has 3 hydrogens, whereas H2O has 2 hydrogens. But the NH3 has a structure that looks like this. It has a hydrogen here, which has a positive side, a hydrogen here, which has a positive side, and then you could think of a hydrogen coming kind of out of the page, maybe. This is a common way of drawing it, coming out of the page with a positive side, and then you have 2 electrons on this side of the nitrogen, so you have a negative side here. And so the NH3, which is ammonia, is also polar. So these 3 are polar, and the CH4, with its nice tetrahedral structure of hydrogens, is nonpolar. And here for our own education, this is basically what a helium atom looks like. You have inside of it 2 neutrons and 2 protons. The 2 protons are what defines it as helium, and they are very tiny inside of the nucleus, and then the 2 electrons form an electron cloud around that nucleus. And so this is basically what a helium nucleus looks like. And it's very nice, very stable, reacts very little with anything else. You have to get to pretty extreme situations before you actually find a reaction that helium participates in. Helium is a noble gas. For all intents and purposes, you could almost, if you're going for 100 on this Regents, maybe you may understand that extreme situations make noble gases react. But if you're not going for 100, like if you're like, really struggling to pass, working on maybe passing and getting that 80, then it is worth just going ahead and assuming that helium doesn't react with anything at all. It is a noble gas. Really very rare to see it reacting with anything else. Like so rare that we just pretend that it doesn't react with anything at all. In fact, it's one of the last elements to have been discovered because of the fact that we didn't really find it in many things. But of course, eventually we found it. Number 10, given the equation representing a reaction F plus F to F2, which occurs during this reaction, is energy absorbed or released? Though that's choice 1, 2, 3, and 4. So this is a 2 by 2 problem. And then is a bond formed, or is it as the bond is formed, or is it as the bond is broken? So this is again a 2 by 2 question. So why do I call it a 2 by 2 question? You don't have to draw this diagram. I did talk about why I call it a 2 by 2 question earlier, but this is kind of the thing. You could think of each part of the question separately, but one part of the question is where's the pen? There we go. Is the energy absorbed, or is energy released? Okay, and then is a bond is formed, or is a bond broken? And so you don't have to draw this box every time. In fact, I recommend you don't draw the box at all. But this, for illustration purposes, I do want to draw it this one time. So choice 1 is where energy is absorbed and a bond is formed. Choice 2 is energy is released and a bond is formed. Choice 3 is that energy is absorbed and a bond is broken. And choice 4 is that energy is released and the bond is broken. So what we could do is we could ask our question separately, whether the energy is absorbed or released, and also separately whether a bond is formed or broken. The one that I think is the most obvious is, so this is in the forward direction, right? So which means that in that direction, we have two individual fluorines that bonded to make F2. So this is clearly a bond is formed. So I put a checkbox on choice 1 and 2, put a cross around 3 and across 3 and 4. Now a checkbox next to the problem means that it could be the answer. Again, bond formed, bond formed, bond formed. And I cross out next to the answer if I think it's wrong. But in this case, since I know that a bond is broken, is not broken, choice 3 and choice 4, I could cross it out at the number. So you could use my notation. It's really simple notation. A checkbox next to the answer, if you think it's right, you circle it when you know it's right. And then you put a X next to the answer if you think it's wrong, and you put an X on top of the answer choice if you know it's wrong. So in this case, I know choice 3 and choice 4 are wrong. Choice 1 and choice 2 have one bit of correct information, and then I go to the second piece of information. And it is important to know that when this compound is formed, energy is released. Okay, so energy is in fact released, not absorbed. Okay, which crosses out choice 1 and 3 and leaves choice 2 and 4. But the only one that has two checkboxes is choice 2. So that's the answer. 2 by 2 question. And with that, we finished the first 10 questions of this Regents out of 85 questions. I'm really stoked. I'm excited. And with that, though, we're going to go to number 11. Based on table S, an atom of which element in group 16 has the greatest attraction for electrons in a chemical bond? Is it oxygen, sulfur, selenium, or tellurium? And with this is our actual first foray into the reference table. So let's go to the reference table. Let's go to table S. And now we are looking for the which of these numbers is going to tell us the attraction for electrons. Let's just take a quick look at the table. Properties of selected electrons and selected elements with the atomic number here, the symbol here, and the name here. So we don't have to go and memorize these number symbols and names. We could actually just go by the table, and then which of these numbers then tells us the attraction for the electrons, and the electron attraction is determined by the electronegativity. Okay, so we are looking for the element with the highest electronegativity. So we look for oxygen, and we see an electronegativity of 3.4. Okay, 3.4. We look for sulfur, which has here an electronegativity of 2.6. Let's actually zoom into this a little bit so we can see it a little bit better. 2.6. Then the selenium, which has an electronegativity of here 2.6 also. And then the tellurium further down, here it is, 52, with an electronegativity of 2.1. So suppose you were a student. Let me just talk just a little bit briefly about test taking strategy. Suppose, because we are trying to not just. Some of you are trying to get 100 on this Regents, and in fact, even those of you who are like getting 40s on the Regents and you're just trying to pass, you should actually be aiming for 100. So you should be aiming to learn as much as possible through this video. So suppose though you were struggling, this is a test taking strategy, and you knew that the electronegativity was the number that was relevant for determining which element has the greatest attraction for electrons, and you notice that the electronegativity for these numbers are 3.4. This is too thick. Okay. There you go. 3.4 and 2.6 and 2.6 and then 2.1. And you didn't remember which one of these, like the higher one or the lower one, was the one that gave you the highest greatest attraction for electrons. But you notice that selenium and sulfur are in the middle. So by test taking strategy, we know that choice 2 and choice 3 are wrong. So even if we don't know what the answer is, we now have a 50-50 chance of getting the question right. The reason I wanted to talk about this in this problem is because I get to talk about now a passing problem. What do I call a passing problem? What I call a passing problem, if we go back to the browser, but we go to the conversion chart between these grades, you'll notice that to get 100, we have to get 85 questions right, but to get a 65, which is the passing grade, that's a 50 points, which happens to be exactly the number of multiple choice questions on this test. However, the bigger point is that 50 is just a hair above half the points. 42.5 points is half the points. And so 50 is slightly above half. And so what happens is if you get some points here and there through other strategies, then you really need only about half the points on this test to get a passing grade. And so if you get to a multiple choice question and you eliminate 2 choices, now you have a 50-50 chance of getting it right. Every single question in which you have eliminated 2 choices with 100% certainty means gets you to a situation where that problem statistically neither raises your grade nor lowers your grade if you have to wild guess after eliminating 2 choices. That's why it's called a passing problem. That said, other test taking strategies might get you to the point where you could do even better. Okay, so now going back to the test again, what is electronegativity? Electronegativity is literally that number. It's a number which represents the attraction for electrons in a chemical bond. In a chemical bond. So this is literally the electronegativity. So you want a higher electronegativity. So the higher electronegativity is the one that makes the most sense. 3.4. Another way that you could have analyzed this problem is by going into the periodic table. And if you happen to recall this is a really good, useful piece of information. The bond between the oxygen atoms in O2 is much stronger than the bond of the sulfur atoms in sulfur, stronger than the bond of two atoms in selenium, stronger than the bond of two atoms in tellurium. And then as you go down to polonium, the bond between two atoms is actually very small. Polonium is in fact more likely to be found bonded to other things than it is to polonium atoms. So that said, the bond up higher for oxygen is significantly higher than the bond for tellurium. Okay? Let's go on, though, to the next question, which is number 12. A solution is made by completely dissolving a sample of sodium, a hydrogen carbonate in water. This solution is classified as a heterogeneous compound, heterogeneous mixture, or homogeneous compound, or homogeneous mixture. So the fact that it's dissolved, completely dissolved here, that's the key word here, completely dissolved. That when something is completely dissolved, you get a homogeneous mixture. So heterogeneous means separated. Separable? Yes, separable. And not perfectly mixed. So this one, homogeneous, is more correct. And is it a mixture or a compound? When you take the sodium hydrogen carbonate in the water and dissolve it, this did not say that the two compounds, the water and the sodium hydrogen carbonate, reacted. It does not say that they reacted, so they do not have a chemical compound. This is they're not a chemical compound. These are a mixture. So mixture are unbonded constituents. So choice 4 is the answer. Number 13, in which sample of matter can the proportions of its components be varied? Cl2 gas, Br2 liquid, or KCl solid, or KBr aqueous? Again, can the proportion of its components be varied? So in Cl2 is pure. So the components, this is pure chlorine. And this is also pure bromine. So there is no variation that actually can occur in terms of its chemical components. Now the KCl, that is two different atoms, potassium and chlorine, bonded to each other. It's a salt. This, though, because of the chemical formula of it, KCl, this is the balance is the proportion, rather, not the balance, the proportion is 1:1. Whereas this one, what about this one? The proportion of KBr, you might say, is also 1:1, but because it's aqueous, so the proportion of KBr, potassium bromide, and water can change. Can be changed. Just add more water or add more potassium bromide. So it is choice 4. In fact, this is asking about the fact that this is an aqueous solution. That's the key to this question. Number 14, according to the kinetic molecular theory, the particles of an ideal gas have an attractive forces between them, or random constant straight line motion, or a greater size than the distance between them, or collisions that increase the total energy of gas particles. So let's just be clear about what the kinetic molecular theory is. We assume that there are no attractions between the particles. That's a big assumption for the kinetic molecular theory. Okay. Does it mean that there are in real life no attraction between the particles? No. No. There could be attraction, there could be repulsion, there could be attraction or repulsion depending on the orientation. But in the kinetic molecular theory, the very starting point of these theories, before we add any complications, there are no attractive forces between them. The second thing, the collisions between the atoms are assumed to be minimized, so they have a smaller size than the distance between them. And in fact, in the basics of kinetic molecular theory, the very first assumptions is that there are no collisions, which would imply that they're smaller. Again, the collisions that increase the total energy of the gas particles, the collisions do not change the total energy of the gas particles. Okay? So in kinetic molecular theory. Okay? So that the collisions are elastic. So what about the rest of it? The motion in basic kinetic molecular theory, the motion is assumed to be random. Absolutely true. And the constant, that's why the collisions don't change the kinetic energy of the gas particles. And straight line motion, it's not even parabolic. It just goes one direction, bounces off the wall, goes in the other direction, and that's it. So this is the big assumption for kinetic molecular theory. Number 15, a chemical reaction is most likely to occur when reactant particles collide with the proper orientation and the proper charge, energy, mass, or volume. So of course the charge is something relevant, but this is already assuming that the particles have a fixed charge to begin with, and then they're colliding. What is the biggest determinant of whether the reaction occurs? The orientation has to be appropriate, but also the amount of energy of the constituents, the amount of kinetic energy between the two has to be high enough for the reaction to occur. Because if the particles come together but they don't have the right amount of kinetic energy, they don't have the ability to overcome that activation energy required to make the reaction occur. So energy, they do have to have the right amount of energy. Charge, though relevant, is not a variable that changes for two particles over extremely short timescales. The mass is not the determining factor, in fact, of the reaction. The mass doesn't matter as much as what the actual chemical is. And then the volume of the particle is usually fixed. So the volume of the particles doesn't matter. And so and just to be clear, why we can eliminate these choices, the reason we can eliminate volume is that the volume, this is asking whether the volume is the variable that makes two particles react. And that would imply like two molecules that are the same size are equally likely to react with another particle. That's not true. The chemical composition matters more. Or that the mass matters more. And again, that's not true because the chemistry periodic table is arranged based on reactivity, which is largely but not completely, but largely determined by the electron shell configuration. And so we talked about the chemical 16 elements, sorry, I said chemical 16 elements, but not the group 16 elements, that they tend to react in a somewhat similar way. You know that the group 18 elements are the noble gases, and they tend to pretty much not react at all. The electron shell is the most important determinant of that. And of course, the mass varies as you go up and down the periodic table. And of course, the charge, again, if we that would for that to be the variable, that would imply that if the charges of the two particles is exactly the same, then the reaction is equally likely to occur, and that's not the case. But the energy between the two particles is the determining factor. The orientation of the particles and the energy, absolutely. So that's it. And here, in fact, I brought in this chart, where this is representing the potential energy. Potential energy of two substances, okay? And this says with a reaction without enzyme, an enzyme is a catalyst. But the difference between an enzyme and a catalyst is just that an enzyme is a catalyst that will appear, let's say, in a biological context, whereas a catalyst can appear in any chemical context, including enzymes. And so what happens is reactants come together, and these two reactants are trying to react together. They come in and with this amount of energy, in fact, this specific amount of energy, and then they get bonded together and form a product. But in this chart, we see that the activation energy is lower, but the activation energy is a function of the reactants. So how could the activation energy be lower for two reactants? The answer to that question is that if an enzyme or a catalyst participates in the reaction, the catalyst lowers the activation energy for the reactants, and so it makes the reaction be more likely to occur and occur therefore at a faster rate. So that's how catalysts behave. But notice that the energy. Notice that in this case, if you notice the shape of the molecule, this is kind of representative of the orientation having to be just quite right for them to actually merge. Okay? Number 22, atoms of which element bond with each other to form chains, rings, and networks? Chains, rings, and networks. Is it calcium, carbon, chlorine, or cobalt? And this is a super important one to know. Carbon has this property. Carbon chains, as in hydrocarbons, or rings, as in sugars, or networks, as in graphite. Okay? So carbon. This is just a really important one to know. So we hop right over to carbon and know that is the case for carbon. Okay. Number 23. I mentioned graphite, also graphene. Okay. Which is a very important, currently strongly being researched form of carbon. Number 23. A molecule of which compound contains an OH functional group? Is it propanamide, or 1-propanamine, or propanal, or 1-propanol? And good luck if you actually know the answer to this question, but for this we go to table R of the periodic table. So let's go to table R of the periodic table. Okay. Table R. Here's table R. And we're looking for a OH functional group. And actually, this table is organic functional groups, class of compounds, and functional group. So we look for the functional group OH. It says hydroxyl group. And that's an alcohol. And in fact, they did us a favor by giving us an example of an alcohol. And the example that they gave is 1-propanol. So which one has a functional group? Has to be an alcohol. And they gave us the example of 1-propanol. And if we go back to the test, in fact, has 1-propanol as the answer. So it has to be an alcohol. And the example on table R that they gave is 1-propanol. So there's our answer. Ethanol is yet another answer. Okay. 1-propanol is the example that the test gave us. So any alcohol ends in OL. Number 24. Which statement explains why butane and methylpropane are isomers of each other? Is it that they have the same molecular formula and the same structure, or they have the same molecular formula and different structures, or they have different molecular formulas in the same structure, or they have different molecular formulas and different structures? So if you happen to know what category of compounds these are, butane and methylpropane, these are alkanes of, yes, alkanes. So, if you happen to know that, then you might actually be able to identify their molecular structure just based on the name. However, that's not something that is really super emphasized in chemistry class, and it's a very large possibility that you don't know how to do that. So I do want to address that. And I will address the chemical structures of both of these because they're not so complicated. And it's something that is expected to be able to be done in further problems. But this problem is asking us to identify what an isomer is. And that's really what this wants us to know. Isomers are compounds with the same molecular formula and different structures. Structures. So, what is the structure of methylpropane? Has a carbon, and a carbon, and it has in the middle carbon, it has another carbon coming out of it, okay, and then it has hydrogens. Let's zoom in here. So I'm writing over these letters, but okay. Hydrogen's coming out of here. Okay, hydrogen's coming out of there. Hydrogen coming out of there. So all of these are hydrogens. Okay. H, H, H. And you could also call this one 2-methylpropane, but methylpropane, since the only place for a methyl group to bond to propane is the second carbon, you could also just call it methylpropane. Okay, so notice the number of carbons that this has. It says 4 carbons, and it has how many hydrogens? 3, 3, 3, and 1. 3, 3, 3 is 9 plus 1 is 10. So C4H10. There's butane, which I'm going to draw in green. Has 4 carbons, and with hydrogens coming out of there, out of every carbon. Notice that all of these have a single bond, okay? And so this is butane, and notice that this has also 4 carbons, C4, and 10 hydrogens. And so they are isomers of each other. They have the same molecular formula. And so if you happen to know that isomers have the same molecular formula, then you can cross out any that have different molecular formulas, cross out choice 3 and 4, leaving us with a passing problem, choice 1 and 2. But what makes them isomers, though, is that they have different structures. Different structures, different chemical properties. So choice 2 is the answer to that. Number 25, molecules of which two substances each contain a multiple covalent bond? Is it ethene and ethane, or ethene and ethine, or methane and ethane, or methane and ethine? And this actually is something that we could look up in table Q of the periodic table. And if so, let's go to that. Okay. And here it is. Okay. So the alkanes have formulas that follow this model, CnH2n plus 2. And notice that these all have single bonds. All alkanes have single bonds. Okay. Then alkenes have a double bond somewhere along the way. Two carbons are bonded to each other. Okay, and this is an example of ethene. And then an alkyne, like ethine, for example, which is included here, has a triple bond between the two carbon atoms. So notice that in the answer choices, we have ethene and ethane, which they actually gave us that as an example. Ethane has only single covalent bonds. So methane also has only, because it's an alkane, only single covalent bonds. Where ethine has a triple covalent bond, and ethene has a double, so covalent. And so the only one that has two that has multiple covalent bonds is choice 2, ethene and ethine. Ethene has a double covalent bond, and ethine has a triple covalent bond. Who came up with these names? I actually don't know. If you happen to know, do post it in the comments. I would love to know who came up with these names. Ethane, ethene, ethine. And I mean, pronunciation wise, they can sound the same sometimes. So I wonder why they chose those sounds. Maybe, I don't know. But whoever came up with the names, I would love to know. Feel free to post it in the comments. Number 26, which term identifies a type of organic reaction? Deposition, substitution, solidification, or vaporization? Now this one, I feel like this question could have been earlier in the test, although it's number 26, which means it's starting to approach some of the more difficult questions. Okay, but I do feel like this one could have been earlier in the test. But because what do these words mean? So a deposition happens when a gas cools immediately to a solid. That's deposition. Solidification is when a liquid is cooled and then forms a solid. Vaporization is when a liquid is heated and then forms a gas. Whereas substitution, this is a type of chemical reaction. So not only is it possible for an organic reaction to be or not only is a substitution a type of organic reaction, it's the only one that is a chemical reaction. So the others are actually physical reactions. These are reactions to change in potential or kinetic energy of the individual particles as opposed to bonds. So choice 2 is the only one that actually has the only one that is a chemical reaction. So that is the answer to this question. Number 27, which statement identifies where oxidation and reduction occur in an electrochemical cell? Both oxidation and reaction occur at the anode, or both oxidation and reduction occur at the cathode, or oxidation occurs at the anode and reduction occurs at the cathode, or oxidation occurs at oxidation occurs at the cathode and reduction occurs at the anode. Okay, so I do want you to know that if you happen to remember a little bit about how electrochemical cells work, the oxidation and reduction occur on opposite sides, anode versus cathode. So it can't be that they both occur at the anode. We can cross that one out, okay? And they can't both occur at the cathode. We can cross that one out, okay? So I remember when I was in high school, my teacher gave us this acronym, Red Cat and anox. Cat and ox are animals, so red cat and ox was easy to remember. And so what does this acronym mean? It means that reduction occurs at the cathode, and oxidation occurs at the anode. Anox, okay, anax and red cat, okay. So the one that matches that is choice. Oxidation occurs at the anode, reduction occurs at the cathode, is choice 3. 28, which type of reaction yields a salt and water as the only products? Is it combustion, fermentation, neutralization, or polymerization? So salt and water. Salt and water. How are salts produced? It's helpful to think about it in the specific example of NaOH plus HCl react to form NaCl plus H2O. And this is a very classic example. This is in fact, NaCl is in fact table salt. That's salt that you use in your food. And it's also the salt that makes the ocean salty, taste salty. But also it's helpful to know because HCl is an extremely strong acid. And NaOH, sodium hydroxide, is an extremely strong base. And so the acid and base react to form a salt plus water. And so if this reaction does it, then what kind of reaction is this? Is it combustion, fermentation, polymerization, or neutralization? What is combustion? Combustion is a reaction with oxygen. And which produces heat, so fire. Fermentation is a reaction of yeast. This is the main type of fermentation that you will see. Yeast convert sugars to alcohol. Yeah, there are other types of fermentation, but this is a main one. Polymerization. This is a reaction that creates long chains between atoms, usually or often carbons. I'm going to take away the word usually and put often. And so neutralization is then looking like a good answer. It's a combination of an acid and a base to form salt and water. And so neutralization definitely fits a salt and water byproduct reaction. Number 29, in which process are heavy nuclei split into lighter nuclei? Nuclear fission, nuclear fusion, or single replacement or double replacement? So single replacement and double replacement are chemical reactions. In a single replacement reaction, one atom or ion is replaced by another atom or ion. And in a double replacement reaction, it's kind of more like a trade, where two atoms or ions are traded between each other to form two new. So two compounds react to form two new compounds. Okay. So those are chemical reactions where a heavy nuclei splitting into a larger nuclei, heavy nuclei split into lighter nuclei. This is a nuclear reaction. So we can eliminate choice 3 and 4, which gives us a passing problem. But now which one is it? Fusion, I want you to know this, that fusion combines lighter elements and fission. So fission, F-I-S-S-I-O-N. So fusion is the combination of two things. So fusion is the combining of lighter elements into heavier elements, and fission is a breaking up. So fission breaks up heavier elements like uranium into lighter elements. And so this one is saying heavy into lighter, heavy to lighter. And the only way to do that is if you take the heavier elements and make lighter elements. You could do that by breaking them up. This is a nuclear fission. Number 30, which statement explains the large amount of heat produced during a fission reaction? Chemical bonds are broken, or chemical bonds are formed, or energy is converted to mass, or mass is converted to energy. Again, fission reaction is, once again, it's a nuclear reaction. This is not a chemical reaction, so not a chemical reaction. So, which is nice, because even if we don't know the answer, we can eliminate choice 1 and choice 2, which gives us a passing problem. But now, which one is it? Which explains the large amount of heat produced? Is it that energy is converted to mass, or mass is converted to energy? So the heat is energy produced. So the energy is produced, so which means that mass would have to be converted into energy, and that does happen. If you take the unfizzed reactants, measure their mass, and then let them fizz, let them break up into smaller nuclei, and then measure the mass after the fact, you would find that the mass has gone down. And unlike chemical reactions where the mass for all intents and purposes doesn't change. We don't even talk about it that way in chemistry class. In physics, in nuclear reactions, the mass change is significant enough that it's measurable. So the mass is converted into energy. That is true. Okay. And here, just for interest's sake, we talked about the bonding to each other to form chain rings and networks. This is essentially the chemical structure, the crystal structure of diamond. The crystal structure of diamond. Now, it's important to know the yellow is for visual purposes, okay? These yellow bonds, or is it green? I'm colorblind. The green bars are for visual purposes. They're not bonds. I had to look really hard to find one that didn't show those bars as the same color as the actual bonds. And I think the people who created the ones that have like the bonds and which are in gray and white here, and the bars which are in green here, most of them have them the same color. And I think the people who created them think that they are bonds, and it's not. It's just that this crystal structure is repeated in diamonds. So if you take one of these structures and put one to the left, to the right, in front and back, and above and below, and then kept doing that, that's what diamond looks like. So this structure is repeated across the entirety of a pure diamond. Okay? And with that, we get to celebrate getting a perfect part A on this Regents. We've gotten 30 questions correct, and we've aced part A, which is phenomenal. With that, we're actually going to take a snack break. So if you are interested in getting a snack, like if you're listening to this at home because you got the Regents tomorrow, then definitely take the video with you and keep watching it while you get your snacks. You use it to get a bathroom break, whatever it is. Real quick, I just want to briefly talk about snacks. I didn't bring all my snacks with me, but one of the snacks that I brought for myself, I brought coffee for myself with mostly milk. I used an instant coffee. But to this, I'm a professional coffee drinker. I've been drinking coffee for years, decades. So if you're not a professional coffee drinker, and you know you're not a professional coffee drinker, for example, if you put more than 2 sugars in your coffee, if you put 6 sugars in your coffee, you're not a professional coffee drinker. I recommend not bringing coffee to the test other than decaf. If you never drink coffee, I recommend not even using decaf. This milk that I put in here is also lactose free, so it doesn't cause any amount of like bloating or anything like that, which is great because you don't want to end up having to use the bathroom halfway through the test because you drank some coffee. Another one that I recommend is one that I love, Fairlife milk. Okay, and Fairlife does not sponsor this video, but I recommend it because it's a small amount of liquid, so it eases your thirst without making you have to use the restroom in the middle of a test. It has a lot of protein, which makes you feel more full. And it doesn't have a lot of carbs or fats, which doesn't give you that much energy, but at least it takes away the hunger, which takes away a distraction. And another, I don't have one of the bars here, but I do recommend pure protein bars, or really any bar that you prefer, as long as it doesn't have lactose in it. Okay, really any bar out there is perfectly good. The other thing I do recommend is no bars that like flake off and make your test messy. You don't want that on your test. It should be a bar that stays clean while you're eating it. And with that note, we are actually going to hop over to part B1. Now, part B1 is actually extremely similar to part A. So you may or may not even notice the differences between part A and part B1. It's all part B1 is all multiple choice questions for this chemistry test. Number 31. What is the approximate mass of an ion that has 12 protons, 13 neutrons, and 10 electrons? The approximate mass. So what is the mass of a proton? So the masses, one proton has a mass of 1 atomic mass unit. One neutron has the mass of 1 atomic mass unit. And a 1 electron is so light, it's less than 1,000th the mass of a proton and less than 1,000th the mass of a neutron. It has essentially 0 atomic mass units. Electrons have an extremely tiny effect on the mass of the whole particle. The mass of the whole particle is largely determined by the nucleons. So what is the approximate mass of an ion that has 12 protons, 13 neutrons, and 10 electrons? The 10 electrons don't affect the mass significantly. The mass is determined largely by the number of protons and the number of neutrons. 12 plus 13 is equal to, according to my calculator, 25. So 25 units. Number 32, given the bright line spectrum of element X and the spectra of 4 mixtures, so I do take a quick look at the bright line spectra, and I see element X, mixture A, B, C, and D, and I see the bright line spectra. I see a bar, and I see mixture A has certain bars, mixture B has certain bars, mixture C has certain bars, and mixture D has certain bars. And it says which mixture contains element X. Is it mixture A, B, C, or D? So the bright line spectra, they're essentially like a fingerprint, really, for the element. So the bright line spectrum of these elements can be used to determine which elements are in the sample. And the way that the bright line spectra are created, the bright line spectra, essentially electrons are shot at the sample. And the reason it's done that way is that you want to give the electrons in the orbitals of the sample energy without giving it in a way that we can visibly see the light. If we shine the light at them, then the spectrum may be drowned out by the light that we shine at them. But there are ways to get around it, and I'll talk about that after. But you shoot electrons at it. The electrons then impart energy onto the electrons in the orbitals of the mixture, and then including element X, but including other things, and then those electrons drop down to lower orbitals, and when they do that, they also release a very fixed, specific amount of energy that is dependent on the energy difference between the two orbitals. So electrons bombard the sample. They give a certain amount of energy to the particles in the mixture, and then including particle X, and then the electrons in the mixture, including particle X, drop down, emitting a very specific fixed amount of energy at a specific wavelength. And so the answer to this question then is the one that has the same exact bars as element X. Okay? And if we look for the one that has the same exact bars as element X, we see element X bar here. We see element X bar here. We see element X bar here. And we see element X bar here. And do we see other bars in mixture B? Absolutely. But it has all the bars for element X. So that means that, and mixture B, in fact, is the only one that has those. So mixture B is the sample that has element X. Now, why do we do it that way? Why do we bombard the sample with electrons as opposed to bombarding it with light? If you bombard it with white light, you can get a dark band spectrum, interestingly, because what ends up happening is the elements, including element X, absorb the photons of light, and then they emit them in random directions. So the white light doesn't quite reach us. However, the reason it's not normally done that way is that the sample is usually pretty small. So as a result, the absorption spectrum may not be bright enough or really dark enough for us to be able to see it with our eyes or even with machines. Whereas the bright line spectrum with a sample could be made arbitrarily bright by essentially just bombarding it with more and more and more electrons. So you could have a small sample and still get a good bright line spectrum. Anyway, so the only one that has the same lines as element X is mixture B. Therefore, mixture B is the answer to number 32. And with that, we move on to number 33. What is the number of valence electrons in an atom in the ground state with an electron configuration of 2, 8, 18, and 3? 2, 8, 18, 3. Now, we can go into the reference table and see which one actually fits this. However, we actually don't need to do that because they actually gave us the electron configuration. But if we did want to do that, we can go into the reference table and see 2, 8, 18, and 3. So this would be a period 4 element with 3 electrons in the outer shell, and that would be scandium. That said, that's not necessary in this case because they gave us the electron configuration. They gave us that the final shell has 3 electrons, so the number of valence electrons of this atom is 3. Number 34, which statement describes the general trend in electronegativity and atomic radius as the first 7 elements of period 3 are considered in order of increasing atomic number? Is it that electronegativity decreases or does it increase? And then separately, does the atomic radius decrease or increase? And this is a 2x2 problem in combination of those two questions. And it turns out that this question can be answered with the reference table. If we go to the reference table, period 3 starts at sodium, and they told us to do the first 7 elements. So from sodium to chlorine. And then if we go to table S, so this is a table S question, we could actually see the trends in both electronegativity and atomic radius. So this is something that is valuable to know, but it is given to us in the reference table. And let's see what the electronegativity says. From sodium to chlorine, we see that it goes from 0.9 to 1.3, 1.6, 1.9, 2.2, 2.6, 3.2. Very clearly increased electronegativity, increasing electronegativity, and they actually do also give us the atomic radius. So the atomic radius goes from 160, 140, 124, 114, 109, 104, and 100. So we see that the atomic radius actually decreased. So the answer to the question, the electronegativity increased for sure. Cross out decreases. So we cross out choice 1 and choice 2. And then the atomic radius definitely decreased, not increased. So cross out any that say increased. And the only one that has 2 check boxes is choice 3. So we have that information from, and let me write that down again, table S. And with that, we go to number 35. What is a chemical name of KClO2? Is it potassium chlorate, potassium chlorite, potassium hypochlorite, or potassium perchlorate? And this is actually a reference table question. When I was a kid, this is just something we had to memorize, but this is table E of the reference table. So let's actually go to table E. So again, potassium chlorate, chlorite, hypochlorite, or perchlorate, and the chemical is KClO2. We go to table E. Table E. There we go. And so let's see, potassium chlorate. So that would be ClO3 minus. So potassium chlorate would be KClO3. Potassium chlorite would be KClO2. Potassium hypochlorite. Where's hypochlorite? Well, first perchlorate, I found that one first. Potassium perchlorate is right here. So that would be KClO4. There it is, right above it. Hypochlorite, KClO. So if we go back to the test, we can write those down. So this is a reference table question. KClO3, KClO2, KClO, and KClO4. And so they wanted KClO2, potassium chlorite, is choice 2. Number 36, what is the percent by mass of oxygen in CH3COOH, where the gram formula mass of CH3COOH is 60 grams per mole? Is it 27%, 32%, 53%, or 60%? Now, with a little bit of knowledge of the reference table, it is possible to eliminate some of these choices. Like, for example, knowing that the gram formula mass of hydrogen is just about 1, okay? Whereas the gram formula mass of carbon is, did I go too far? Carbon is about 12, and the gram formula mass of oxygen is about 16, okay? So, so if we go back to the answer, we know that the two oxygen in CH3COOH have a mass of 16 each, whereas the carbons have a lower mass than oxygen, 12, and then the hydrogens have a mass of 1. So if you add up the numbers, the oxygen has slightly more mass than the carbons, and the hydrogens have a very small mass. So the answer is going to be very close to 50%, and also likely more than 50%, eliminating choice 1 and choice 2. So even if we don't know how to do the problem, we've actually arrived at a passing problem. And now, just in the words that I said, I'm starting to suspect that choice 3 is more likely to be the answer, and choice 4 is less likely to be the answer, because I think the answer is going to be very close to 50%. So I noticed my marks over here. I've crossed out choice 1 and choice 2 at the numbers because I know those are wrong. I put an X next to 4 because I think it's wrong, and I put a checkbox next to 3 because I think it's right. So that's a very easy way of marking the test that you could take from me, that you could easily track what you think or know for a problem. But how do I do the problem numerically? The gram formula mass, of oxygen is 15.9994. We saw that from the reference table, okay? But, which is around 16. Now, why can I use the 16 instead of the 15.9994? Because really, technically, I have to use the 15.9994 in general. But the reason is that we are working with two significant digits, 60 grams per mole gram formula mass of the CH3COOH. So I can actually work with the 16, and I see that there are two oxygens. 16 times 2 is equal to 32. And so the percent mass of oxygen is 32 over the full mass is 60. Multiply that by 100%. You're not expected to know how to do this on paper. You don't have to do this on paper. But you do have access to a calculator. However, this does imply that the answer is very close to this. And in fact, this is, 30. If you wanted to do some math, 30 over 60 plus 2 over 60, which is 1 over 30, which is that times 100, 100 over 30. So anyway, so the point is rounds to 53%, okay? And that I would definitely do on a calculator. On that note, let's go to number 37. Given the formula for a compound, C, I see a carbon, I see two hydrogens and an oxygen double bonded here. How many electrons are shared between the carbon atoms and the oxygen atoms in a molecule of this compound? So you want to know that a bond, like for example, if you have O and an H here, a bond, this is a covalent bond. But it doesn't even have to be a covalent bond, so I'm just going to erase that covalent bond. But a bond, it contains 2 electrons. Okay, so since there's two bars here, that implies that there's 2 times 2, which is equal to 4 electrons. And that's the number of electrons that are shared between these two compounds, between these two elements, carbon and oxygen in this compound. Okay. On that note, I wanted to talk about the emission and absorption spectrum of a substance. These are the emission and absorption spectrum of two different substances. You'll notice that the colors go from violet to blue to like a green, yellow. Cyan is somewhere in there. Cyan looking color is in there. Yellow, then orange and red, and then fades to essentially black when it goes into the infrared, which we can't see visually. But what causes the emission and absorption spectrum? This is a lot like number 32 that we just discussed earlier. So the difference between the emission lines and the absorption lines, they have the same essential cause. The essential cause is that in a sample, the electrons can only absorb really very specific amounts of energy. In fact, that's actually the reason why when we talked about compounds forming, when in a collision of two particles, they don't just have the right orientation, they also have to have the right amount of energy. And if they don't have the right amount of energy, both too little but also too much, within reason, also too much, then the reaction doesn't happen. Well, the same thing happens with the electrons in the orbitals of a atom or compound. So the electron orbitals each have a certain amount of energy. So for an electron to hop from one orbital to another, it has to have a very specific amount of energy, okay? Or it has to have a specific amount of energy absorbed. And when that electron hops from a higher energy level to a lower energy level, it also emits that exact same amount of energy, which means that it emits a photon of exactly one wavelength or frequency, or one color. And so the emission lines are bright because the energy is given to the electrons through collisions with other electrons. Yes, there is a photon essentially absorbed, but the reason why that happens is more interesting to the physics class, because where did the photon of light come from in a interaction between two electrons, right? But that is on the physics side how it's described. The electron, electron beam interacts with the electrons in a sample. That causes the one electron in the sample to go up, and then when that electron comes back down, it emits a very specific wavelength of light, which might, in this case, have been either red or green or blue or approaching violet over here. And so what about the absorption lines? Well, the absorption lines happen because the electrons are kicked up to higher orbitals. Instead of through interactions with electrons, they're kicked up by interactions with actual photons, white light. So you shine white light at a sample, and then the particles in the sample absorb very specific wavelengths of light that will kick up an electron to a higher energy level. Then when that electron drops back down, it re-emits that photon, but it can re-emit that photon in some random direction instead of the direction of the white light. And so the sample leaves behind a dark band where that light was initially absorbed, and then it re-emitted in some random direction, not towards your eye. So the cause of the band is the same, but the source of the energy changes the way the line looks. When electrons kick up electrons into other higher orbitals, then they emit photons that you can then see. And even though they're scattered in random directions, some of the light goes to your eye, so you see a bright line. Whereas there is no other light it being shown anywhere, or even absorbed anywhere, so you see a dark band there. Whereas here, there is just a sample of white light, maybe from a bulb, and some of that energy is absorbed by electrons when they're kicked up, and then re-emitted in some random direction, not towards your eye, so you see a dark band. Okay, on that note, we hop over to number 38, okay? And it says, which particle model diagram represents the arrangement of particles in a sample of neon at STP? The circle represents an atom of neon. Is it choice 1, where everything is in a random place? Choice 2, where individual neons are bonded to each other, but they're still floating in random places? Or choice 3, where they're all in a cluster, all kind of in the center, kind of like a solid? Or choice 4, where they're all at the bottom of the container, but kind of spread around at the bottom of the container? And for this, you do need to know a little bit about the structure of neon. So if you go to the periodic table, you'll notice that neon is the second of many noble gases. So because neon is a noble gas, and because its electrons are very nice and symmetric, the attraction between neon atoms is extremely low. So neon has an extremely low boiling point, and at STP, neon is a gas. Okay? So if you go back to this sample, this one here represents a solid. This one represents a liquid. This represents a polyatomic gas. But neon is a noble gas, right? Again, neon, noble gas. So you wouldn't find, at STP, you wouldn't find neon in any of these three configurations. Choice 2 would have been right if they said oxygen. Choice 1 is correct because they said neon. Number 39, the volume of a 150.0 kilogram sample of copper at 298 Kelvin and 101.3 kilopascals, which is standard pressure, is 16.7 centimeters cubed. That's the volume. The mass of the copper sample is expressed to how many significant figures? So we have to talk about how significant figures work. Okay, so let's just have a quick conversation about significant figures. Okay, so what is a significant figure? First off, so significant figures. What can I write there? Or yeah, let's write there. Significant figures. And here's the thing: non-zero digits are always significant. And then the zero digits, literally the number zero, the number zero, okay, follows the acronym NADS, N-A-D-S, never, always, and decimal significant, okay? So N, so leading zeros are, I'm going to write a zero. Leading zeros are never significant. Okay. Zeros between a non-zero digits are always significant. Okay. And then the DS, zeros at the end of a number are only significant if there is a decimal. So trailing zeros, zeros at the end of a number, and then leading zeros, again, the leading zeros are zeros at the beginning, okay? So the zero, so remember this again, the non-zero digits are always significant, and then the zeros in a number follow the acronym NADS for when they are significant or not. And so let's give an example of two different numbers. Let's say 5003800, that's a large number, versus 0.091103900. Okay, so there's just these two numbers, and we want to know which ones are significant. We said that the non-zero digits are always significant. Okay, so let's highlight those. Non-zero digits are always significant. So this 3 is significant, this 8 is significant, this 5 is significant. And in this number, the 9, the 1, the 3, and this 9 are all significant. And then the other ones, the zeros satisfy the NAD acronym. So leading zeros at the beginning of a number are never significant. And then the zeros, the zeros between digits are non-zero digits are always significant. That's in this color. So these zeros are between non-zero digits. So these are always significant. And this one is also always significant, because it's between the 1 and the 3. So I'm going to go and highlight that one to match this dark cyan to be a light cyan. Okay, there we go. And then finally, the zeros at the end. The zeros at the end are only significant when there is a decimal. So the D, there is no decimal here. There's no D. So not significant. And here there is a decimal. This one starts with a decimal. So the zeros are significant. So the NADS acronym. And so these last trailing zeros are significant. So if you want to know how many significant digits there are, this one has 5 significant digits or significant figures. And this one has 1, 2, 3, 4, 5, 6, 7 significant digits. And so going back to this one, going back to the problem, it talked about how many, the mass of the copper sample is expressed to how many significant figures, the mass. So we're looking at the mass, 150.0. So leading zeros, the non-zero digits, the 1 and the 5, are significant. Let's actually do some highlighting here. Now I'm going to highlight in one color. The 1 and the 5 are significant. Now there are no leading zeros. There's no zeros in the front. There are no zeros between digits, but there are trailing zeros, and there's a decimal. So the zeros are also significant. Decimal significant. Decimal significant. DS. So leading zeros are none. The zeros that are in between two numbers It happens to be that there's none in this problem. But any zeros in between two non-zero digits are always significant. And here, there's a decimal. There's two of them. Because there's a decimal, so the two zeros are significant. So in total, that there's 4 significant figures in this answer. Number 40, which statement describes the energy transfer that occurs when a sample of copper at 100 degrees Celsius is placed in a sample of water at 20 degrees Celsius? Is thermal energy transferred from the copper to the water, or thermal energy is transferred from the water to the copper, or chemical energy is transferred from the copper to the water, or chemical energy is transferred from the water to the copper? Chemical energy happens in chemical reactions where bonds are formed or broken. And when the copper is placed in the water, there is no chemical reaction that happens between the water and the copper. In fact, the one difference between these two samples is their temperature. So the chemical energy is not the answer to this question. So we could eliminate choice 3 and 4. We have a passing problem, which is great. Now, thermal energy is transferred from the copper to the water, or water to the copper. Thermal energy goes from an area, from a hotter area to a cooler area. Since the copper is at 100 degrees Celsius, which is hotter, and the water is at 20 degrees Celsius, it's cooler, then the energy transfer is happening from the hotter thing, which is the copper, to the water. So thermal energy is transferred from the copper to the water. Number 41, which change will cause an open flask half filled with water at 295 Kelvin and 0 atmospheres to reach phase equilibrium? Is it increased in temperature, increase the pressure, or increase the temperature, or remove some of the water, or seal the flask with a stopper? So phase equilibrium is representing the solid, liquid, or gas phase. This is not a chemical reaction. So notice the key thing here is the open flask. Why did that happen? So the open flask. So what happens to the water if the flask stays open? Well, the water keeps evaporating. So if you increase the pressure, the only way to increase the pressure in the flask is to increase the pressure of the whole room. That's not feasible. But it also doesn't prevent water from changing from liquid to gas by just evaporating. Increasing the temperature will cause it more water to evaporate, but it's an open container, so it'll just keep evaporating until it's done. So this doesn't do it, this doesn't do it. Removing some of the water doesn't change any facets of this system other than the amount of water that will eventually evaporate. But if you seal the flask with a stopper, then the amount of water evaporating from the water, from the liquid water, will equal the amount of water going from the gaseous state and condensing onto the liquid water. So sealing the flask will definitely do it. Number 42, what is the amount of heat released when 1.0 moles of NH3 is formed from its elements at 101.3 kilopascals and 298 Kelvin? So this is room temperature and standard pressure. Is it 45.9 kilojoules, or 91.8 kilojoules, or 137.7 kilojoules, or 183.6 kilojoules? So if you happen to know this or answer, that's great, but you really do need details about how this reaction occurs. And so this is actually a reference table question. And if we go to the reference table, if we look at table I, let me write that in my notes, table I, and we actually see a reaction between N2 gas an H2 gas. Right here, N2 gas plus 3H2 gas forms 2NH3 and releases 91.8 negative. So the delta H is negative 91.8 kilojoules, which is releasing 91.8 kilojoules of energy. So let's actually write that down in our test. So N2 plus 3H2 reacts to form 2NH3. All of these are gas, plus an amount of energy released equals 91.8 kilojoules of energy. And so immediately we may be gravitating towards that exact answer, but we have to look at, in this reaction, going back to the reference table, we have to look at the details of that table, and it says the heats of reaction at 101.3 kilopascals, but the assumption is that the reactants are the number of reactants or products is the number of moles of reactants or products is equal to the coefficient. Okay, so that means that here this is actually 2 moles of NH3. And so to figure out the amount of energy released when 1 mole of the product is formed, we have to actually divide the 91.8 kilojoules divided by 2. What just happened there? The 91.8 divided by 2, which is equal to 45.9 kilojoules. Number 43, given the equation representing a phase change for carbon dioxide, CO2, so CO2 solid plus energy forms CO2 gas, which statement describes this phase change in terms of energy and entropy? Is the phase change endothermic or exothermic? And does entropy increase or decrease? So this is a 2x2 problem once again. So the one that I know is, I know that an entropy is a measure of disorder. Entropy is a measure of disorder. So a sample that is more disordered has a higher entropy. And so the question is, which one is more disordered? A solid sample of carbon dioxide or a gaseous sample of carbon dioxide? In a carbon dioxide, a solid sample, all the atoms are arranged in some specific form and they are not free to move. Whereas in a gaseous sample, the particles are completely free to move. So this is an increase in entropy. So that actually tells me that entropy can increase, entropy does not decrease, entropy can increase, entropy does not decrease. Choice 2 and choice 4 are wrong. That gives me a passing problem. And against what I said was entropy is a measure of disorder. And so then, is the phase change endothermic or is it exothermic? Well, the carbon dioxide, according to this reaction, energy is on the left side of this reaction. So according to this reaction, energy is absorbed by the carbon dioxide. So this is endothermic. Endothermic energy is absorbed. So endothermic makes sense. Exothermic, it does not make sense. Exothermic energy is released. Endothermic energy is absorbed. The only one that has 2 checkboxes is choice 1. So 43 is, the answer to 43 is choice 1. Number 44, which equation represents an oxidation half reaction? Is it Br2 forming 2 Br negative plus 2 E negatives? Or Br2 plus 2e negatives forms 2Br negatives, or Mn2 plus 2e negatives form Mn, or Mn react to form Mn2 plus 2e negatives. So it helps to know what an oxidation reaction, half reaction is. So an oxidation half reaction means that the reactants, the reaction is what would happen when reacting with oxygen. And so oxygen has the only oxidation state of oxygen listed in the reference table is, let's go to the periodic table. The only oxidation state that's listed for oxygen is -2, meaning that the oxygen gains 2 electrons. So if something is reacting with the oxygen, then it is then the half reaction is that the oxygen would be gaining the electrons, so the reactants would be losing electrons. And so here, the first one, let's just be clear about the first one. We're starting with neutral bromine and ending up with two negative bromines and 2 electrons, which means that the charge is not balanced. So this half reaction doesn't even make sense. But this one, in choice 2, the bromine, each bromine is gaining an electron, which is not what happens when oxygen reacts to it. Remember, oxygen steals 2 electrons. This bromine is gaining 2 electrons, or bromine, in other words, is stealing 2 electrons. So, or each bromine is stealing 1 electron. This is actually a reduction. And by the way, the reason it's called a reduction is because the charge is going down. So it's a reduced charge, lower charge. So that's not it. The third one here, once again, the charge is reducing. I'm sorry, the charge is going down. The Mn2 plus ion is gaining an electron. So that's the opposite of what happens when it reacts with oxygen. The only one that loses an electron is this last one. This is an oxidation. And yeah, manganese can react with, each manganese atom can react with 1 oxygen atom to form manganese oxide. And this is oxidation reaction. Okay. Number 45, which equation represents a redox reaction? So what is a redox reaction? A redox reaction is reduction and oxidation reaction. So, and what happens to that? That means that the oxidation states of the reaction of the reactants changes. So let's look at the oxidation states on the left and the right. The oxidation state of the carbon is 0. The oxidation state of these two oxygens is 0. And the oxidation state of the carbon here is +4. The oxidation state of each of these oxygens is -2 and -2. That's a change. The calcium here, +2 and -2 for oxygen. The hydrogen plus and then -2. And then the products, we end up getting a +2. And the same deal, -2 and +1 times 2. And the same, if you go down the list again, the same thing happens all the way down the list. So but we've already determined that in the first one, the oxygen reacts with carbon. Each oxygen gains 2 electrons. The carbon loses 4 electrons. So the oxidation state of each of them changes. So that's the one that makes the most sense. Okay. Number 46. Based on table J, which metal will react spontaneously with Fe+2, iron +2, aqueous ions? Is it copper, gold, magnesium, or silver? Copper, gold, magnesium, or silver? And they were nice and told us the exact table. They said table J. So let's go to table J. Here's table J. So the question was again, which metal will react spontaneously with iron +2? So so the metals go in order from most active on top to least active on bottom. So if we look, copper is down here. Gold is here. Silver is down here. So these are the 3 least reactive metals. They are far less likely to react to the iron and definitely won't react spontaneously. But if we look for magnesium, magnesium is actually extremely reactive. Despite the fact that it's kind of low, it's just that lithium and all these other metals are extremely, extremely reactive, but magnesium is also extremely reactive, very high up in the most active part of the series. So magnesium is the answer that makes the most sense for this problem. So magnesium is the answer. These are the 3 least reactive metals. Copper is so unreactive that it actually can be found in its pure atomic state in nature. And as of course gold and silver can also be. But if you notice, gold is actually the least reactive of all the metals on this list. Which is why gold and silver are used to make jewelry. It's also why copper is also used to make jewelry, but then copper tends to do things that are annoying in jewelry. So number 48, given the equation representing a system in equilibrium, so HSO3 negative aqueous plus H2O liquid reacts in both directions with SO3 2 minus aqueous plus H3O plus aqueous. According to one acid-base theory, let's see, HSO3 minus acts as an acid because it is an H plus donor, or HSO3 minus acts as a solid acid because it's an H plus acceptor, or H2O acts as an acid because it's an H plus donor, or H2O acts as an acid because it's an H plus acceptor. So first off, let's look what happens in this reaction. H2O reacts to form H3O plus. So H2O accepted NH plus. And in fact, the HSO3 minus reacted to form SO3 minus 2, so the HSO3 donated an H plus. Okay, so two of these can be eliminated. Choice 3 says that H2O was an H plus donor. It wasn't. It was an acceptor. And then the choice 2 can also be eliminated because this one says that HSO3 minus acts as an acid because it's an H plus acceptor. It's not. It's an H plus donor. And so that leaves choice 1 and choice 4. Granted, if you're struggling in chemistry, maybe you skipped a lot of chemistry classes, and if you did skip a lot of chemistry classes, do take it as a lesson that in the future, when you get to physics and when you get to future classes, don't skip those classes. It's really important to be at there. And if you're wondering the definition of too many classes skipped, actually 1 per month is actually the limit beyond which we can, in research, see a significant low reduction in content knowledge. So if you're missing more than 1 class a month, you're missing too many classes. Okay? That said, what makes an acid, what acts as an acid? So an acid does what, if you think about what regular acids that you've thought of do, like HCl, for example, HCl reacts and releases that H plus, which means that acids donate H pluses. So which one donated an H plus? The HSO3 donated an H plus. Okay. Number 49. What is the pH value of an aqueous solution with a hydronium ion concentration 1,000 times greater than an aqueous solution with a pH value of 5.0? Is it 1.0, 2.0, 8.0, or 14.0? This one does require a little bit of knowledge of chemistry. I don't think that anywhere on this test, and I'm just doing a quick scroll, I don't think that anywhere on this test, I don't think they talk about how the pH is calculated. And in fact, I confirmed here that they don't talk about the concentration of hydronium ions. So we do have to talk about that. So the pH is equal to the logarithmic concentration of the H plus or H3O plus ion, the hydronium ion. And it ends up being the exponent on 10. So like if the concentration is equal to, let's say, 10 to the, it's actually the negative. If the concentration is equal to 10 to the negative 5, then the pH is equal to negative log base 10 of 10 to the negative 5, which is equal to positive 5. It's the exponent, the positive version of that exponent. And so when the hydronium ion concentration is 1,000 times greater than an aqueous solution with a pH value of 5, notice 1,000 times greater, that's 10 to the third times greater. And the exponent on 10 to the third is a 3. So the hydronium ion concentration ends up going to 10 to the notice, okay, so 10 to the negative 5 is a smaller number. We have to multiply 10 to the negative 5 by 1,000, 10 to the 3, and that's equal to 10 to the power of negative 5 plus 3, which is equal to 10 to the negative 2. That is something that you can determine on your calculator, by the way. You could do log base 10 of parentheses 10 to the negative 5 times 1,000 and take the negative log of that, and that spits out a negative 2, and you negate that and you get a positive 2. So the pH is 2.0. And we got one more problem before we get a passing grade. Which energy source is paired with a risk associated with its usage? Nuclear fission produces stable isotopes, or nuclear fission produces radioactive waste, or voltaic cells produce stable isotopes, or voltaic cells produce radioactive waste. And so, again, radioactive waste and stable isotopes, chemical reactions have no effect. Have no effect on isotope stability, nor do they have an effect on radioactivity. We separate chemical reactions from nuclear reactions in chemistry class. They're very separate. So voltaic cells are chemical reactions. So chemical batteries, you have one in your phone, you have one in the computer that you're watching this, wherever you're watching this. So those are not the answer. They don't have an effect on the radioactivity or stability. So this one, now we have a passing problem. We've eliminated two choices. But does nuclear fission produce stable isotopes, or does it produce radioactive waste? Again, this is, risk. If it produced stable isotope, that wouldn't be a risk. But radioactive waste is that's a very big risk. It makes some people be very, very anti-nuclear energy. I am not one of the people who's anti-nuclear energy, by the way. I am actually very pro-nuclear energy, because the thing is that we kind of, it's like the danger that we see versus the danger that we don't see. We know what the dangers of nuclear power plants are. We've seen a very small number of nuclear accidents out there. But Chernobyl being one, Fukushima in Japan is another one. Those are the dangers that we see, and of course we know what nuclear weapons are. But the dangers that we don't see, the power plants that work off of coal, they release a tremendous amount of soot and, generally speaking, pollution. And so what ends up happening in those situations is that we breathe those in, and other animals breathe those in, and that causes cancer. And we don't see that, but it does turn out that those reactions have a much bigger effect on our health than the risks than the accidents that have occurred with nuclear power plants. So the radioactive waste is a risk. But that said, I am a supporter in increasing nuclear energy. I did put this in for just a quick summary of some acids and bases that you've seen. Tomatoes are acidic. Soda is very acidic. Lemons are very acidic. And lead acid batteries, of course, or nickel and lithium ion batteries. A lot of batteries that you use are acidic. Some basic substances, baking soda is basic, and if you add it with water, it increases the pH. Toothpaste is actually basic. It's made that way to neutralize some of the acids that form in your mouth when you are just living, existing, or sleeping. And then drain cleaner is a great example of a basic substance. On that note, we get to celebrate getting a perfect B1 and also passing this Regents with a 65. Number 50 got us a 65 on this Regents, but of course, we are not working towards a 65. Even if you're struggling and you really just want to pass this Regents, you and I, neither of us are working just towards a 65. We're working on learning as much as we can for this test so that we can get 100. And notice that just focusing on the multiple choice, like a lot of people recommend, is physically not possible on this chemistry test because we got every single chemistry question multiple choice right, and that only got us to a 65. So we really do have to put immense amounts of focus on the part twos as well. I'm saying part twos because I'm talking like in the math classes where it's like part twos, threes, and fours. But no, we have to focus on the part B2 and C, and do as well as we can in those as well to get us the best grade possible. So we, with that, are going to go on to 51, and generally speaking, part B2. So the big difference between part B1, B2 is that now we are actually at short answer questions. The rest of the test is going to be short answer questions, and so we have to give sentences or calculations as our answers. And we still have to use the reference table as normal, so that's not too surprising. But with that note, we're going to hop over to number 51. It says to state in terms of electrons and energy states how the light emitted by excited boron atoms is produced. So we talked about that in the emission spectrum before. The energy is absorbed by electrons in the orbitals of the boron. That causes the electrons to hop to a higher energy level. The photon itself is a particle of energy. So that energy is electromagnetic radiation. That particle is absorbed. That gives the electron a higher energy. It goes to a higher energy level. Then that electron then hops down to lower energy levels and emits a photon essentially or equal to in wavelength and frequency and energy to the energy difference between the energy levels. So in the case of this question, it's saying state in terms of electron energy states how the light emitted by excited boron atoms is produced. And then you could say that of the electron drops from a higher energy state to a lower energy state and emits a photon. Okay, now for the rest of this, using this is a part two. This is a part B2 question. Now we have combo questions. So that's what the instructions say. I'm not going to zoom in on the instructions too many times because they're going to repeat. But we want to base our answers to question 52 and 53 on the information below and our knowledge of chemistry. The atomic mass and natural abundance for two naturally occurring isotopes of copper are shown in the table below. It says naturally occurring isotopes of copper, isotopes copper 63 and 65, atomic mass 62.93 and 64.93, and natural abundance 69.15 and 30.85. And I don't internalize those numbers completely, but I always read the table before I read the problem. Number 52, show a numerical setup for calculating the atomic mass of the element copper. Again, the atomic mass is actually not just the mass of just a single atom or pure isotope of that atom, but it's actually a weighted average of the natural abundance of that element in nature. And in this sample, so we the atomic mass, we have to do a weighted average. So we do the atomic mass 62.93 times the natural abundance 69.15 over 100 plus that. So that's the fraction of naturally occurring copper. That's copper 63. Plus then copper 65 has a mass of 64.93, and its abundance is 30.85 over 100. And that's all they want. They don't actually want you to write down the number. They just want you to write down that calculation, which is phenomenal. In another question, they could have asked you to plug that number into the calculator and then to give that number, but in this question they didn't. But how would you get this answer? I mean, now that we have the expression, we would literally plug it into the calculator and we would get the answer. So that's it. Number 53, a technician determined the percent abundance, natural abundance of copper 65 in a sample to be 31.47. Determined the percent error for this percent natural abundance of copper 65 compared to the accepted value shown in the table. So the table has the accepted value. The technician determined the 31.47. So how do we do the percent error? It's percent error is equal to the expected minus the actual, put that in parentheses, divided by the actual times 100. And so then we write down this calculation. And this one, they do expect us to give the answer. So let's see. The expected is the 31.47. That's what he actually got. Minus the actual natural abundance of copper 65 is 30.85. Divided by the actual 30.85 times 100. And then we have to put that into the calculator. And I did put that into the calculator with those parentheses. And I got 2.010%. And so that is the answer. And they actually accepted any answer between like 2.0% and 2.01%. So 2.010% is the answer that the calculator spit out for me. I gave it to 4 decimal places because 4 significant digits because all of the numbers given had 4 significant digits. Now these instructions, again, they're going to repeat, so I'm not going to keep zooming in and zooming out just for video non-editing sake. The element, but we want to base our answers to 54 through 56 on the information below and our knowledge of chemistry. The elements beryllium, magnesium, calcium, strontium, and barium are located in group 2 of the periodic table. These group 2 elements have both similarities and differences in their physical and chemical properties. Number 54 says, based on the location of group 2 elements in the periodic table, state the element classification of these elements. Group 2, so they did tell us that they're group 2 elements, and unfortunately the reference table doesn't tell us the name of this group per se, okay, but they were very kind, in my opinion, very kind in terms of what answers they allowed for this question. Like for example, if you just said metals, they would give you points. The exact so some groups that are helpful to know. So group 1 are the alkaline metals. So this is now just giving you extra details. Group 2, I'm going to put this one in green. Group 2 are the alkaline earth metals. And then for some reason my teacher, I don't know why, only gave me 4 names, but group 17 are the halogens, and out of curiosity, I just checked to see if there were other names and for the groups, and there are some other names. Group 3 through 12 are the transition metals. So group 3 to 12 are the transition metals. And then finally, group 18 are the noble gases. Okay, so, and it turns out that group 16, obviously 13 through 16 are missing. I have here group 16 are called the chalcogens, which I've never used nor heard of that name before in my life. So I didn't write it down. Chalcogens. So, but that said, what did the question ask for? The question asked for the group 2 elements. And so this is the answer, alkaline earth metals. So if you said alkaline earth metals, you would have gotten a point. In fact, again, they were very kind and allowed you to say just the word metals. So if you just said metals, number 54, they would have accepted that. Number 55, explain in terms of electron shells why the atomic radius of a calcium atom in the ground state is greater than the atomic radius of the magnesium atom in the ground state. So this is in terms of electron shells. So we have to look at the calcium and the magnesium. So we have to, here's the calcium here in period 4, okay? And here's the magnesium in period 3, and they're both in group 2. So the only difference in atomic radius is the fact that they're in different groups. I'm sorry, different periods. And in fact, the number of periods corresponds to the number of energy levels. So in terms of electron shells, in terms of electron shells, calcium has 4 electron shells, while magnesium only has 3 electron shells. The more electron shells that you have, the bigger the radius of the atom, the bigger the radius that the atom has. Number 56, state the general trend in first ionization energy for the group 2 elements beryllium through barium, as these elements are considered in order from increasing atomic number. The first ionization energy of group 2 elements from beryllium to barium. So like if we look at group 2, beryllium to barium. So if we go into the reference table, theoretically we would ideally want to know it. In fact, when I took this test, when I took the AP, I don't recall if that giant reference table had that information, but this one does. The first ionization energy. So let's see, beryllium, first ionization energy 900. Then the next one is magnesium. Magnesium, first ionization energy 738, which is lower. So it looks like it's going lower. Calcium. Now what I'm doing, you see me scrolling very quickly, but what I'm doing is going to the reference table and seeing what the next element is. So, well, there it is, calcium. 590, even lower. And then if we go to I'm going to go to one more, strontium. SR. 549. So they did go down, and if we did keep going through the rest of the reference table, we would notice that the first ionization energy would continue to go down. So that's actually what we have to say as the atomic number in group 2 elements increases, the ionization energy, the first ionization energy decreases. Nice. So we didn't have to know that by heart. We could have gone to the reference table, and in fact, we just did. For completeness sake, I did I decided to bring this diagram. I don't know why this diagram pasted here instead of earlier. Oh, I know why I pasted it here, because it talked about isotopes. That's the reason. So this is an example of a fission reaction, which does occur and is asked about earlier in the test. But the fission is occurring between hydrogen 2 and hydrogen 3. So the red represents a proton, and the gray represents neutrons. So this H2, this 2H represents a hydrogen with one neutron and one proton, of course, and this particle on the right represents a hydrogen with one proton and two neutrons. So that there's different isotopes of the same element, and they happen to fuse together in the hearts of stars, and currently also we're trying to make a nuclear reactor with hydrogen that so far takes a lot of energy to run. So we'll see if it ever works. I think it will eventually, but the end results are helium and just an enormous and a neutron, and also an enormous amount of energy. But here, this hydrogen and this hydrogen, they're both isotopes of the same element. Okay. Let's see. And by the way, I have these subscribe buttons all over the place. You could subscribe if you feel like I deserve it. If you feel like I don't deserve it, if you've made it up to this point in the video and you feel like I don't deserve it, don't subscribe. But if you feel like I do deserve it, please do. If you feel like this video is helping you, please do say that in the comments. Let me know that this video has helped you, so that because that is a big motivator for me. I love to know that what I'm doing, this is a free service that I'm providing, and I would love to know that this is helping you. Okay. Number 50. Now we're going to base our answers to questions 57 through 59 on the information below, and again our knowledge of chemistry. Diagram 1 represents a sample of N2 gas and the conditions of pressure, volume, and temperature of the gas in a sealed rigid cylinder with a movable piston. The conditions are here. And diagram 2 represents a sample of O2 gas and the conditions of pressure, volume, and temperature of the gas in a sealed rigid container with a movable piston as well. And compared to the average kinetic energy of the gas molecules in diagram 1, compare the average kinetic energy of the gas molecules in diagram 1 to the average kinetic energy of the gas molecules in diagram 2. I noticed that diagram 1 has a sample whose temperature is 300 degrees Kelvin, and sample 2 has a temperature whose of the sample of 300 degrees Kelvin. So they have the same temperature. And if they have the same temperature, they have the same average kinetic energy. In fact, the temperature is literally a measure of the average kinetic energy of a substance. That's literally what temperature is. So if two samples have the same temperature, they have the same average kinetic energy. Number 58, determine the volume of the O2 in diagram 2 when conditions are changed to STP. So this one, there is a formula. Let's actually look to see the formula sheet on the reference table here, all the way at the end. There is a formula sheet here. This is the combined gas law. This is under the assumption that the number of molecules does not change. If the number of molecules does change, you get a slightly different equation. So, but there's just an N1 and an N2 in the denominator, and that's the difference. But so this is a combined gas law, P1 V1 over T1 equals P2 V2 over T2. It is on the formula sheet, so they can give you problems with the formula. So this one again is P1 V1 over T1 is equal to P2 V2 over T2, and then plug in some numbers, So they said determine the pressure when the two conditions are changed to STP. So the original conditions are 60.0 kPa, right? The original volume is 1.8 liters. The temperature is initially 300 point Kelvin, and that's equal to P2V2 over T2. And that's the big deal about this formula. So what's they said it's STP. So there's a P2, which is again standard pressure, and kPa is 101.3 kPa. The volume is a mystery number, but it's a mystery number, and it's okay that we don't know it because, well, we're looking for it. And then divided by standard temperature, which is 0 degrees Celsius or 273 Kelvin. If you use 273.15 Kelvin or 273 Kelvin, either one of those is a valid choice of numbers. Okay, so there is our formula. Okay, and if we go, by the way, to the top, well, I mentioned that the standard pressure and the standard temperature are the numbers that I gave, but the test does, the reference table does give you the standard temperature and the standard pressure as part of table A. So you can, if you don't remember what STP is, go to table A. Okay. So table A, that's STP. And then P1V1 over T1 equals P2V2 over T2, and we plug in those numbers. And so how do I go about solving this equation? I go and I cross multiply. That's how I teach it, okay? I cross multiply. Now that I have the units, I don't have to rewrite the units over and over. So I could write 60, 1.8, 273 equals 300, 101.3, and V. So now I'm going to divide by 300, and I'm going to divide by 101.3, divide by 300, divide by 101.3, those cancel, and I get a volume approximately equal to, now I do put all the numbers down and then I round after the fact, 0.970187561 liters. And now the reason I write all the digits down and then I fix it later after but on paper is that it's a really quick muscle memory fixer for students who don't remember to round to the right thing. This one, I see that all the numbers have either 3 or 4 or 2 significant digits. The minimum number of significant digits is the 1.8 liters. So 2 significant digits. So I'm going to give it to 2 significant digits, 0.97 liters. So there is my answer. And they accepted anywhere from 0.970 to 0.983. And I'm not sure where the 0.983 comes from, but 0.97 is a perfectly valid answer. Okay? Now we're going to base our answer to 60 to 62 on the information below in our knowledge of biology, of chemistry rather. The boiling point for a sample of a molecular compound is 80 degrees Celsius, and at standard pressure, the heat of fusion, HF, of this compound is 127 joules per gram. Compare the potential energy of the molecules in the sample before vaporization to the potential energy of the molecules after vaporization. So the thing that makes liquids different from gases of a specific sample is literally the potential energy. So like in a sample of liquid water, the atoms, the molecules of water have actually a negative potential energy. That's why they're stuck down in the liquid phase. Then you give them enough potential energy to escape the liquid. So you give them enough energy to escape the liquid that potential energy goes from negative to zero, and then you give it additional energy to kick up the kinetic energy so that it can fly away from the liquid. So that so the potential energy of molecules in the sample before vaporization to the potential energy of molecules after vaporization. So what I said is that each gram of liquid has less potential energy than each gram of gas. Okay, and in fact, it's actually a negative versus a zero. It really is a negative versus a zero. The potential energy of a gaseous particles is zero, and the potential energy of liquid particles is negative. Okay. So number 61, determine the amount of heat required to completely melt a 50.0 gram sample of this molecular compound at its melting point. So we know that we know the heat of fusion, and we know the mass. So it's important to be able to label the things that they gave us. So this is the mass, and this is the heat of fusion. So it makes me wonder if the reference table has a formula relating the heat of fusion, the heat of vaporization, and the energy. So here, or the change in energy, and here it is at the bottom of the last page. You have Q is equal to MHF. Okay, so there's a formula for us. Q. Let's zoom in a little bit differently. There you go. Q is equal to MHF. So the mass. They want to know the heat required. So Q, we're looking for Q is equal to. And then we're looking for a Q. So is equal to 50.0 grams times HF, 127 joules per gram. And we multiply these two out on a calculator, and we get 6350 joules. And that's our answer. All right, let me erase this box because I need to be able to read the next problem. Number 62. Explain in terms of intermolecular forces why the boiling point of this molecular compound is lower than the boiling point of water at standard pressure. So in terms of intermolecular forces, it's important. Water would have a much lower boiling point if it weren't for the really strong hydrogen bonds attracting the water molecules. The attractive forces between the molecules, the attractive forces between the water molecules, the hydrogen atoms in the water, and the oxygen atoms in the water. That strong hydrogen bond is what keeps water in a liquid phase for such a long time, for such a high temperature. If in a different sample of something else, if the intermolecular forces were lower, then the boiling point would actually go down because a smaller force would need to be overcome in order to boil away. So that's what we could say. We could say that the molecules of of this compound have a lower attractive force than that of water. So a great example is like alcohol. Ethyl alcohol boils at like in somewhere in the 70s, I believe, Celsius. So one of the reasons is that ethyl alcohol is not nearly as polar as water is. So it ends up having much lower intermolecular forces, and so it can boil at a lower temperature. And here is a diagram of a bunch of water molecules. The big red O's for oxygen, and the smaller white balls for hydrogen. And you see that there's this like weird symbol, delta minus and delta plus. The point is that the oxygens have a net negative charge on the outside, and the hydrogens have a net positive charge on the outside. So the hydrogens and the oxygens are attracted to each other because opposite charges attract. But the same thing is happening on this side of the hydrogen to this oxygen, and on this side of the oxygen to that hydrogen, right? And then this side of the oxygen to that hydrogen. It's really, and it's quite a strong force. Okay, so now we're going to base our answers to questions 63 to 65 on the information below and our knowledge of chemistry. Sodium hydroxide, NaOH solution, and an acid-base indicator are used to determine the molarity of an HCl aqueous solution. A 15.0 milliliter sample of the HCl-AQ is exactly neutralized by 30.0 milliliters of 0.010 molar NaOH aqueous. Determine, first, number 63, identify the positive ion in the sample of HCl aqueous solution. And they were actually conned because they allowed two different answers, the positive ion. The reason that two answers are valid, so H plus is a valid answer because of the reaction that occurs. Or you could have given H3O plus, because in water, that H plus ion does relatively easily react with a water molecule, which to form an H3O plus ion. So either one of these answers would have been valid and would have been worth full credit. Number 64, based on table M, state the color of litmus when placed in a sample of the original HCl aqueous solution. So based on table M, so they don't require us to memorize the color of litmus paper. Yes. So, but they do expect us to understand the pH of an acidic mixture. So we do need to know that a pH of an acidic mixture is lower and the pH of a basic mixture is higher. So since we have an acidic mixture, we're closer down to 4.5. And litmus paper, according to table M, changes from red to blue as the pH transitions from lower to higher. So litmus paper in an acidic solution is red. So the answer to this question, the color of the litmus paper is red. And then number 65, using the titration data, determine the concentration of HCl aqueous in the solution. So we have to, the concentration is a function of the number of molecules. So we have 15.0 milliliters of this sample times a mystery molar solution of the HCl, that divided by the number of milliliters of NaOH aqueous solution that was needed, 30.0 milliliters of a known molarity, 0.010 molar, that is equal to 1. That is equal to 1. So if we do the math here, we could actually, it is possible to do this one without a calculator, but you can use the calculator too. Like for example, you could divide by 15, divide by 15, you get 2, and then you get x molar over, multiply the 2 and the 0.010, 0.020 molar is equal to 1, so that x is equal to 0.020 molar. And that's our answer to this question. And here I brought in a picture of a hydronium ion. So if you haven't seen this big triangular bar, the thing is that when we draw, our paper is, you know, flat. Whereas these molecules tend to be, and these ions, the atoms, the molecules, whatever, they tend to be three-dimensional. So this dark bar, what it represents is a hydrogen atom kind of sticking out of the page. This hydrogen atom is to the left of this oxygen. And then there's a pair of electrons on top of the oxygen. And then down here, this bar represents that this H plus ion, it's an ion, so it doesn't have any electrons at all, is attracted to two of the electrons of the oxygen, forming a bit of an ionic, a bit of, would that even be considered an ionic bond at that point? If the H plus ion already came with a yeah, I guess so, right? It already came to the mixture with a missing electron. So I guess so. So this would be an ionic bond here, and so it forms pretty readily an H3O plus ion. So this is a polyatomic ion here. And with that, though, we could celebrate that we just got a perfect B2, which is super exciting. And in just a few more problems, we are about to get an 80 on this Regents also. Number 70 is going to give us an 80 on this Regents. Notice that relative to some of the other science tests, it takes us a longer time to get to that 80. Number 70 gives us an 80, and then there's 15 more questions to get to 100. So each question after 80 is going to be worth more. Which is great, because if you're hovering around an 80, a little bit of extra knowledge, it will actually improve your grade tremendously. Every extra problem you get right above an 80 actually boosts your grade by 1 or 2 points, which is great. With that, we are now officially in part C, and the last real bit of this test before we get to a perfect grade on the test. And this is the last official part of this test. And number 70 on this page is going to be the one that gives us finally that 80. And so we are almost there. Excuse me. It says to base our answers to questions 66 to 68 on the information below and our knowledge of chemistry. I'm not going to zoom into that just so I don't have to zoom in and out all the time. It says the table below shows 3 compounds that are used for medical purposes. And I do read the table real quick and then I go on to the problem. Formula CaSO4, MgOH2, and ZnO, and the medical uses making plaster cast, antacid for remedy, and protection from exposure to some ultraviolet radiation. Number 66 says to identify 2 types of bonding in the compound used to make plaster casts. Now, in this class, we actually talked basically about 4 types of bonds: ionic, covalent, metallic, and hydrogen bonds. Those are the 4 types of bonds that we discuss here. And hydrogen bonds are between like hydrogen and oxygen in water, or hydrogen and some other chemicals in polar molecules, but mostly hydrogen and oxygen in water, between 2 different water molecules, right? And so it's that doesn't occur with CaSO4, potassium sulfate, because it doesn't have any hydrogen. And then it's not a metallic bond because, well, this isn't a pure metal. SO4 is not a pure metal. Oxygen isn't even a metal at all. So that means that the only 2 remaining types of bonds are ionic and covalent. And so that gives us the answer. So that said, if you go into the reference table, we do have sulfate, SO4 2- is an ion with 2 extra electrons. And in our periodic table, no, it's this one. In our periodic table, we see calcium has the ability to lose 2 electrons. So CaSO4 does form an ionic bond. The calcium and the sulfate form an ionic bond. But the individual atoms in the sulfate, the S, the O, and the O4s, in between them, they do form covalent bonds within that ion. Okay? So ionic and covalent bonds, I don't need to scroll down anymore. Let me minimize this. The only 2 types of bonds that remain, it's not metallics, not hydrogen, so ionic and covalent. Ionic between the calcium and the sulfate, and then covalent between the atoms in the sulfate ion. Number 67, identify the noble gas that has atoms in the ground state with the same electron configuration as the positive ion in MgOH2 minus. Okay, so the same as the positive ion in MgOH2 minus. So we do need to know that H comes in as a plus and OH comes in as a minus. So we got a minus, 2 minuses, and we got Mg plus 2. And so if you look at, back in the reference table, if you look at the periodic table, here's Mg. And if you go back to, because that Mg neutral atom has lost 2 electrons in this case to form an ion, the magnesium had 12 electrons, and then it lost 2 electrons to get 10 electrons, which matches the number of electrons in neon. So the electron configuration of Mg2 plus is the same thing as neon. Has the same electron configuration as neon. If you literally don't give a sentence, if you just say the word Ne, on, or the chemical formula Ne, that would be full credit. Okay? Number 68, based on table S now, determine the electronegativity difference for the bond between zinc and oxygen in ZnO, zinc oxide. So let's go to the table S. Let's go to table S, as it says, zinc and oxygen. Where's zinc? Zinc. Here's zinc. Electronegativity 1.7. And then oxygen is higher up, electronegativity 3.4. So we go to the test, and we do 3.4 minus 1.7, and that's actually equal to 1.7. And so that's our answer. Now we're going to go to base our answers to 69 through 71 on the information below and our knowledge of chemistry. We're about to get an 80. During a laboratory activity, appropriate safety equipment is used and safety procedures are followed. In a beaker, a student dissolves 0.10 moles of potassium nitrate, KNO3, in 100 grams of water at 25 degrees Celsius. The gram formula mass of KNO3 is 101 grams per mole. Number 69, compare the freezing point of water at standard pressure to the freezing point of KNO3 aqueous solution at standard pressure. This is one that does require you to have a little bit of extra knowledge of chemistry when you're coming into the test. So this is an important thing to know. If you have water at standard pressure, it freezes at 0 degrees Celsius. So what happens if you dissolve any salt, not just table salt, but any salt in it? You happen to know, I hope you know, if you live in New York, that if you add salt to snow that it helps to melt the snow. And the reason is that dissolving is an exothermic reaction. Okay, that dissolving is an exothermic reaction. Well, actually, it does depend on the type of salt used. It can be an exothermic reaction and it can be an endothermic reaction. So I do have to pull that back. Some of the salts that you use to melt the snow dissolve with an exothermic reaction, and some of the salts you use to dissolve the snow result in an endothermic reaction. However, why does it end up not mattering that much which version of the salt that you use? The reason is not mattering that much. It does matter, but not that much. The reason is once the water melts, once the water dissolves the salt, the water and salt mixture now has a lower freezing point. So that water and salt mixture will now be in the liquid state, and it could do one of two things. It can run off to somewhere else, meaning the snow won't be where you don't want it to be, on your driveway, on your sidewalk, wherever else. But then the other thing is, since it's already in the liquid state, it's easier for that liquid to then evaporate. And while it's evaporating, more of the snow is also being dissolved and then evaporated. So that's the key reason why putting salt on driveways causes it to not have ice the next day. So do remember that if you add salt to the driveway, the freezing temperature actually goes down. Okay, so that's true for basically every salt. And the cause of that is that actually the intermolecular forces between one of the reasons, there's more than one reason. Entropy is a factor. There's other factors, but one of the reasons is that when you dissolve the salt, which is an ionic compound, in water, the the positive ions would then be attracted to the oxygen freely. The negative ions are then attracted to the hydrogens freely, and so that effectively reduces the hydrogen bonds and the intermolecular forces between the water molecules. So individual water molecules are less able to attract individual other water molecules. Individual hydrogen atoms in one molecule have a less attractive force towards the oxygen atoms in a different water molecule. So it reduces the hydrogen bonds in water. By reducing the hydrogen bonds in water, the molecules in the salt mixture have a lower intermolecular forces, which means that you have to take away more energy in order to get the sample to freeze, and that's why the freezing temperature goes down. So that's what we can say. They're not asking us for the explanation, which is beautiful here. They're just asking us to compare them. So we could say the freezing point of the KNO3 aqueous solution has a lower freezing point, a lower temp. I already said the freezing point is lower. There we go. Better English. Is lower than the freezing point of pure water. There we go. Number 70, based on table G, classify in terms of saturation the type of KNO3 solution made by the student. So we actually have to go to then table G, which is the solubility curves at standard pressure. The solubility curve at standard pressure describes how much of each salt can be dissolved in, how much? In 100 grams of water. 100 grams of water. So just like, for example, at 50 degrees Celsius, you could dissolve approximately 5 grams of SO2, which is really not that much. At 90 degrees Celsius, you could dissolve about 10 grams of NH3. Okay? So we have to find the KNO3 curve. Here's the KNO3 curve. and it's hard to follow with so many curves bunched here. Here's 25 degrees Celsius, okay? So I'm going to follow the KNO3 curve down to about 25 degrees Celsius, which is right around there. It happens to be right around where a couple of different curves cross, but it doesn't matter that a couple of curves cross. We only care about the KNO3. And it's somewhere, if we go to the right, we see the solubility, 40 to 41 grams of solute per 100 grams of water. So we could dissolve 41 grams of solute. So we can dissolve, and let's put that in the test. We can dissolve about 41 grams of KNO3 in 100 grams of water. And let's just make sure, they did say that this is 100 grams of water at 25 degrees Celsius. That's where I got those numbers. Now, how many grams of KNO3 did we actually dissolve? Well, we actually dissolved, it's 0.10 moles. That times the molar mass, 101 grams per mole. That's equal to, well, you could use your calculator at this point. 0.10 times 1.01 is 10.1. 10.1. Let's try that again. 10.1 grams of KNO3. Notice that that's much less than the 41 grams that we could dissolve. So the answer to this question is an unsaturated solution. Let's circle that, dot this I so it's a little more legible. But now we go to number 71, unsaturated solutions. If you said unsaturated or you said unsaturated solution, either one of those would be valid. Number 71, describe in a laboratory procedure the student can use to separate the original KNO3 from the KNO3 aqueous solution. The point is, how do you separate? You can't separate dissolved solution by any process that doesn't add energy to the system. So, for example, you can theoretically separate two different colors of sand by tweezers and much large amounts of time. You can't do that with mixtures because the particles are just entirely too small. So what you need to do here, one thing you could do is you could heat the sample in an open container. What doing that would do is it would heat the water and KNO3. The KNO3 at this temperature is actually a solid. Therefore, the KNO3 would remain, whereas the water, since it's a liquid at that temperature, as you heat it, it would transition some of the atoms in the water from liquid to gaseous state, and it would increase the rate of vaporization, or evaporation rather. So you don't even necessarily have to increase it to boiling point, although to get rid of all the water, you probably would. That said, this is a perfectly valid answer. You could say heat the sample in an open container. You could say heat the water in an open container beyond the boiling point of water. Whatever it is you want to say, that already is enough of an answer. And with number 70 that just passed, and 71, we already are at an 80, and we are approaching a 90, which is phenomenal. I added this problem. The previous problem talked about zinc oxide. And this is individual's face with sunscreen and without sunscreen. On the left side, he has sunscreen. On the right side, he does not have sunscreen. And then in ultraviolet light, you see that the left side it's darker, and on the right side, it's lighter without sunscreen. Now, there are two ways to prevent UV rays from being absorbed in your skin. One is to reflect it away completely, and another way is to have some chemical that you put on your skin absorb the UV rays before they can get to your skin. Which one of those two you use? Well, that's actually kind of up to you. Except that chemicals that reflect the UV rays, I don't know of any personally. There are plenty. I don't know of any that appear in sunblocks. I just don't. But I know zinc oxide is a very cheap, very safe, and a very effective chemical that does absorb the UV rays. And if it absorbs the UV rays, then it doesn't reflect them back, which means that if you looked at a person's face in UV, you would see that they that part of their skin is darker in the UV spectrum. And that's actually what's going on here. You see the left side of this gentleman's face on the, in UV is darker, and the right side of the gentleman's face is lighter. Now, why would you ever only sunscreen half your face? For a photo op. Literally, that's it. This is to demonstrate that sunblock actually does work in the UV, and to prove that sunblock actually does block UVs. But the way that sunblock works is it absorbs the UV rays. That's the way it works. And so, I don't know, are there chemicals out there that you could put that are safe to put on your skin that reflect the UV rays? I don't know. But if they were put on the skin, what we would notice is that the part of the skin where the sunblock that reflects UV rays is on would actually be brighter. But again, not what's going on here. Now we're going to base our answers to questions 72 to 74 on our knowledge of biology and, of course, the reference table and information below. A major component of agricultural fertilizer is ammonium nitrate, NH4NO3. Okay? It is commercially produced by reacting ammonia gas with concentrated nitric acid, as shown in the equation 1 below. Equation 1, NH3 plus HNO3 reacts to make NH4NO3 plus energy. The ammonium nitrate can decompose to produce nitrogen dioxide gas, NO2, which is a brown gas. When NO2 is placed in a sealed glass container, some NO2 molecules react to produce a colorless N2O4 gas. An equilibrium system forms in the glass container, as shown in equation 2 below. Equation 2 says that two NO2 brown gas react in both directions to form N2O4 colorless gas plus energy. Now state, in terms of reactants and products, why the chemical reaction presented by equation 1 is a synthesis reaction. So this just requires us to know what a synthesis reaction is. And a synthesis reaction combines two particles into one particle, and that's it. A synthesis reaction combines two particles into one particle. Okay? That is what a synthesis reaction is. So in this problem, the way we could explain it is that equation 1 combines two molecules into one larger molecule. Larger molecule. Okay? Number 73, on the labeled axes in your answer booklet, draw a potential energy diagram for the reaction represented by equation 1. So I notice in equation 1, the two reactants combine to produce the reactant ammonium nitrate, and energy is released by that reaction. Since energy is released by that reaction, we know that the potential energy has to go down. That is actually the source of that energy. The potential energy of the reactants goes down, and that energy is lost to heat, sometimes to light as well. So here is that graph that appears in the answer booklet, and we the way we graph it is we draw a horizontal line, and then at the point of reaction we draw an increase in potential energy of the activated complex, and that's actually what happens when two chemicals react. They make an activated complex which has a greater potential energy, and then the products are formed. And in the case of an exothermic reaction, energy is lost. That means that potential energy goes down. And so that is a perfectly valid graph right there. The key things to note is that this piece is horizontal and this piece is horizontal. And you want to have a piece where that it goes up initially. And then you want to have a piece that goes down afterwards. And if it's exothermic, your final potential energy has to be lower than your initial potential energy. If the reaction is endothermic, if the reaction is endothermic, then the final potential energy would be higher than the initial potential energy. This second red line would have been above up here. Okay, so that's the answer to that question. Let's put a checkbox here. Let's put a checkbox here. Number 74. Compare the rate of the forward reaction to the rate of the reverse reaction in the equilibrium system represented in system 2. So in equilibrium, the reaction in both directions is exactly equal, like 100% equal. So that's what makes it be in equilibrium. So we just say the word equal here, and we call that one done. Number 74 is done. Now we're going to base our answers to 75 through 77 on the information below and our knowledge of chemistry. Pentane, hexane, heptane, and octane are components of gasoline. The structural formula below represents a straight chain molecule of pentane. And it says to state the number of hydrogen atoms in a molecule of hexane. First off, let's look at this pentane. It's got 5 carbons, and it's got 5 hydrogens on top, 5 hydrogens on the bottom, 2 hydrogens on the left and the right. Each of the middle carbons has 2 hydrogens attached to it, and the end carbons have 3 hydrogens attached to them. And so they wanted us to know the number of hydrogen atoms in a molecule of hexane. And it does turn out that we could get a lot of our information from the reference table. If we go to table P, here are the organic prefixes. The number of carbon atoms in hexane is 6. So according to the reference table, there are 6 carbon atoms. And if you remember from geometry, a hexagon has 6 sides. Hexane has 6 carbon atoms. And so how many hydrogens does a hexane molecule have? Going back to the reference table again, the alkanes, so methane, ethane, pentane, hexane, they all follow the formula CnH2n plus 2. Cn follows the formula against CnH sub 2n plus 2. So if we have 6 carbons, then we have 6 times 2 plus 2 equals 12 plus 2 is 14 hydrogens. So this molecule has 14 hydrogen atoms, okay? 14 hydrogen atoms. Number 76, state in terms of carbon-carbon bonds why octane is a saturated hydrocarbon. In terms of carbon-carbon bonds. So now if you look at the reference table, now the reference table doesn't give us the words, but if you do look at the reference table, you notice that there's ethane, ethene, and ethyne, and alkane, alkene, and alkyne. And the big difference here is the number of bonds between the carbons. Alkenes have a carbon with 2 bonds between the two. And notice that they can technically hold more hydrogens if they would just break that bond. And alkynes have 2 carbons with 3 bonds. And notice that they could add even more hydrogens if they would just break those 3 bonds and form just 1 bond between the carbons. And so a saturated hydrocarbon are the alkanes. The alkanes are the saturated hydrocarbons. And they all have 1 bond between them. And that's actually the answer. So this one says to state in terms of carbon-carbon bonds why octane is a saturated hydrocarbon. And the answer to this is that octane carbon atoms share only 1 bond with each other. You could have said that there are no double bonds. All let me replace the word one with single. Single bonds with each other. You could say that there are no double bonds, there's nor triple bonds, and that's the answer. That's why this is that's why octane is a saturated hydrocarbon. The thing that makes it saturated, well, saturated with what? And the answer is saturated with hydrogens. The other hydrocarbons could react with hydrogens to increase the number of hydrogens bonded to carbons. And so those are unsaturated hydrocarbons. Number 77, draw a structural formula for a straight chain molecule of heptane. This once again, this is once again in table P. We do need to go to table P to get the prefix. Ideally, if you happen to know heptane is 7, great, good for you. But if you didn't remember that, it is in the reference table. Heptane, number of carbon atoms is 7. So we want to draw a structural formula for a straight chain molecule of heptane. We have to draw 7 carbons. C, 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 C. That's 1, 2, 3, 4, 5, 6, 7. Worth your time to count them. 1, 2, 3, 4, 5, 6, 7. One bond between them. And then out of each carbon on the edge has 3 bonds coming out of it for hydrogens, and each carbon in the middle has 2 bonds coming out of it, and all of those are going to be bonded with hydrogen. This would actually be an acceptable answer, but you could also say put the H's in there, and worth your time to make sure that the H's go where the bonds are. And there you go. That is a straight chain molecule of heptane. And now we are about to get a 90 on this test. Number 79. Number 79 is going to give us that 90 on this test. So I'm really excited. And then 6 more questions is going to give us the 100. So we are really approaching a perfect grade on this test. We're almost done. I told you that you could do it. And so I'm really excited about being a part of that with you. And I'm really excited, and I'm really appreciative of you having made it to this point in the video. I really congratulate you for making the effort to make yourself a better chemistry student. So I really mean that. I really want to make sure you know that the effort that you're making right now is going to improve your grade and improve your understanding of chemistry. And that's the big important thing. It's not just about the grade, it's about the understanding. But of course, it's also about the grade, and you're working towards a better grade, and I'm proud of you for making the effort to get to this point. Now, we're going to base our answers to number 78 through 80 on the information below and our knowledge of chemistry. Chlorine gas and sodium metal are 2 valuable industrial elements that can be produced in an electrochemical cell by an electrolysis reaction. Electrolytic reaction. In this reaction, liquid sodium chloride is separated into the elements by an electric current. The simplified diagram and equation below represents this process. In fact, if you happen to have a swimming pool, there's a maybe not a 50-50 chance that you have one of these in your pool. My pool, I put liquid chlorine, but some pools have this where you literally just put table salt in a big machine, and the big machine throws electricity through it and makes chlorine out of it. Yeah, so it's a pretty sweet system. So now we see in this diagram, we have a power source, a plus and a minus. We have the anode, we have the cathode, and the NaCl liquid forms Na plus and Cl minus. And the reaction is 2 NaCl liquid forms 2 Na plus Cl2 gas. Okay. Number 78. State, in terms of energy, why the power source is required for the cell to operate. And so if you think about when you've seen Na and Cl, sodium and chlorine, you rarely ever see them separated. Unless you are in very heavy chemical reaction situations. In fact, you see Na and Cl combined or dissolved all the time. NaCl, again, is table salt, sodium chloride. So table salt is in solid form, an Na atom and a Cl atom bonded through an ionic bond. The Na loses an electron, the chlorine gains an electron, and then they are attracted to each other and they form a crystal lattice. But they're very stable. So to get the sodium and the chlorine to separate, you need to add energy to that system. And that's what we could talk about here. So the NaC, you could say that the NaCl has a lower potential energy than the Na plus and Cl minus separated. And that's probably not surprising that the potential energy of Na plus and Cl minus separated is higher than the potential energy of NaCl combined. If you think about why Na plus and Cl minus combine, it's because of the massive attractive force between a positive ion and a negative ion. Unlike charges, our opposite charges attract each other. So there is a massive attractive force between the sodium ion and the chlorine ion. So when they do combine, they come together, they do so in a way that then reduces the potential energy between those two reactants. That's actually the way that potential energy works in real life. If two particles are attracted to each other, then bringing them together reduces the potential energy of the system. The reason it reduces the potential energy of the system is that the attractive force adds energy to the two particles. So when they combine, the energy is released. Number 79, state the number of moles of electrons lost when 4.0 moles of electrons are gained in this reaction. So there is a way you can do this problem with a balanced equation. Okay, you can do this problem with a balanced equation, but I do think that the best way to do this one is to recognize that the system has to keep a balanced charge. So if 4 moles of electrons are gained in this are lost in this reaction, then 4 moles of electrons have to be gained. If 4 moles of electrons are gained, then 4 moles of electrons have to be lost to preserve charge. That's the law of conservation of charge. Number 80, determine the change in oxidation state that occurs for chlorine in this cell. So here is the chlorine, and the oxidation state, chlorine goes from 0. Chlorine in the reaction, here's the reaction. I was looking slightly the wrong place, so now I'm looking at the right place. The reaction in the reactants, the 2NaCl in liquid form 2Na in liquid plus Cl2 in gaseous form. But here, this is an ionic bond, so we have a Cl minus. And here we have Cl in a covalent bond. So this one, in this one, the chlorine has a charge of 0. So the change in oxidation state is from -1 to 0. So if you just write -1 to 0, you've gotten full credit. With number 79, recall with just the problem before, with writing these 4 moles, we had a 90 on the reagents. And with number 80, we now have a 91 or 92. Let's actually check the reference table to see, now that we've gotten number 80 correct, not the reference table, this sheet, if we've got a 90, a 1, or a 92, and we have a 92, we officially have a 92 on this test. Notice to get a 92 it's not the easiest thing, but if you work hard at it, you understand a lot of parts of the chemistry, you can get a 92 or higher. I believe in your ability to do that. There's just you just get to the point where those minor details are learned, and you can actually get to the point where not only can you get 100, but you actually can practically teach the class because you know even more information than the minimum required for this test. We have a 92, and with number 81 through 85, we are about to get 100 on this region. So I'm really, and a perfect part C. So I'm very excited about it. Thank you for being a part of this video. We are going to jump right into number 81 through 85, a big 5-part question, so base your answers to question 81 through 85 on the information below in your knowledge of biology, of chemistry, not biology. The radioisotope uranium-238 changes to lead-206 in a series of nuclear decays that can be used to determine the age of some rocks. In one step of this nuclear decay series, uranium-234 produces thorium-30 by alpha emission. The graph below represents the decay of a 40 milligram sample of thorium-230. And then the graph says mass versus time for the thorium-230 decay. And I see mass of thorium-230 in milligrams from 40 all the way down to, at this point, 5. And it says 3.0 times 10 to the 5th years. Okay, so that's 10 to the 5th, that's 300,000 years. Good. Now determine the half-life of, using this graph number 81, using this graph, determine the half-life of thorium-230. So what we need to do is to figure out how long it takes for half of the sample to decay. And we can actually go to the graph and see that half of the sample decayed from 40 to 20 in this much time. And how can we write that? We actually can. We don't have to write it in scientific notation, gladly, since this is 3/4 of the 1.0 times 10 to the 5th. We could actually say 0.75 times 10 to the 5th years. So that could be one answer, 0.75 times 10 to the 5th years. Or we could have also said in scientific notation 7.5 times 10 to the 4th years. And just to be sure, if we go another 0.75 years times 10 to the 5th years, we should be at 1.5 times 10 to the 5th years, and another half should be gone, 10 grams. And in fact, if we go to 1.5 times 10 to the 5th is right here where I'm making this mark, and we do see that 10 grams of the sample would be remaining at that point. So looks like that answer is right. We've now got a higher grade, a 93 or 94 on this Regents. We are approaching a perfect grade on this test. I'm so excited. On number 85, we're going to answer it, then we're going to pick up the mic, we're going to drop it, and then we're going to say bye. So number 82, determine the fraction of the thorium-230 sample that remains unchanged after 2 half-lives. And that actually allows us to address a misconception that a lot of students have. A lot of students say, well, if the half-life of the sample is a certain amount of time, then what happens in the second half? A lot of students say that somehow the second half disappears, but that's wrong. And I just want to be clear why that's wrong. The half-life does not say that it's half of the sample all the way at the beginning when you first started measuring. It's whatever the sample happens to be at any specific amount of time, half of it is gone after 1 half-life. And if half of it is gone after 1 half-life, well, then in another half-life, that half that's gone, that half that remains gets cut not completely, but in half. Half of a half remains. So after 1.5 years. So after 1.5 times 10 to the 5th years, or after 2 half-lives. So we go back to the graph and said 2 half-lives is 1.5 times 10 to the 5th years. And we can verify either by multiplying 1/2 times 1/2 equals 1/4, which is the way I did it on my paper, Or you can actually go into the grams and say 10 grams divided by the original sample, which is 40 grams. That's equal to 1 over 4. Again, or you could have said, and I'll put it in a different color, you could have said 1/2 times a half. Half-life, 2 half-lives is equal to 1/4. Or 0.5 times 0.5 equals 0.25. Any of those answers would have given you a point on that question. Jump into number 83, and 3 questions away from a perfect grade on this Regents. Compare the penetrating power of a beta particle to the penetrating power of an alpha decay particle from a thorium-230 atom. And this one does require you to know a little bit of chemistry. Unfortunately, this is not in the reference table. They do want you to know that an alpha particle, being a very large, essentially helium nucleus, this penetrates very shallowly. You could be protected from alpha particles by like a literal piece of paper. Now that does depend on the energy of the actual alpha particle, the energy of the decay. So don't just assume that you could wear a paper suit and protect yourself from every alpha particle. It really does depend on the source of the alpha particles. But if it's a low energy, if it's a alpha particle and a beta particle of the same energy, then relative to each other, this is the decay. This is the penetrating power. This is again a helium nucleus. Oops. So again, an alpha particle and a helium nucleus are the same thing. But what about a beta particle? What is a beta particle? A beta particle is an electron. Why does it have a different name? There was a time that we didn't actually know that they were the same thing. So a beta particle is an electron, and a beta particle, it penetrates deeply. So even though both alpha and beta particles can be dangerous to the human body, a beta particle is getting exposed to beta radiation repeatedly is more dangerous. Okay? And we are 2 questions away from a perfect grade. Number 84, complete the nuclear equation in your answer booklet of U238 by writing a notation for the missing product. And the notation in the answer booklet is just this. It says 238 uranium 92 arrow 4 2 HE plus, and then a blank. And so they want us to fill in that blank. Okay? And if you actually look at the atomic number of the uranium, the atomic mass of the uranium, it's 238, and the atomic mass of the helium, I'm sorry, not even the atomic mass, the mass number. If you look at the mass number of the uranium, it's 238, and you look at the mass number of the helium, it's 4. And so to preserve the mass number of the thorium, of the product has to be the same, so 234. And then also if you look at the number of protons in the uranium, 92, and the number of protons in the helium, that's 2. To preserve the number of protons, we have to have 90 protons in this element. And so is it thorium that this thing keeps talking about? This one was talking about thorium-230, but if you go back to the reference table now, we have to check which element has 92 protons in it. And that would be 92, element number 92 is, I'm sorry, not 92. Did I write 92? With that, we are 2 questions away from a perfect grade on this Regents. I'm super stoked. I'm super excited. Number 84. Complete the nuclear equation in your answer booklet for the decay of U-238 by writing a notation for the missing product. And what is on that page of the answer booklet, I didn't paste it here because of the technology, but the uranium, this is what's written there. U-238, 92, reacts to form helium 4-2 plus a big blank, okay? A big blank, and we have to fill in that blank, and we're going to need the reference table to help us with that. So let's talk about what these numbers mean. The 238 in the uranium is the number of nucleons. It's the mass number of uranium, and the 92 is the number of protons in the uranium. That reacts to form a helium nucleus, an alpha particle, with 4 nucleons, the mass number 4, and 2 protons. So to preserve the mass number, then we could do 238 minus 4 is equal to 234. So the mass number is 234. And then to preserve the number of protons also, to preserve charge, 92 minus 2 protons is equal to 90 protons. So 90. And then we go to the reference table to determine which element that was. So 90, element number 90, is once again thorium, but it's a different isotope of thorium. So TH. It's thorium-234, not the thorium-230 that's above. And with that, we are 1 question away from a perfect grade on the Regents. This is what we have right now. We have a 98 on this Regents. So a 99 is actually not possible on this Regents. You cannot get a 99 on this Regents. The next lowest grade below 100 is a 98. This 1 question is going to get us the 98. So, and then we're going to pick up the mic, we're going to drop the mic, and we're going to be done. So I'm really excited. Explain in terms of elements why the nuclear decay of uranium-234 to thorium-230 is considered a transmutation. So this is a vocab question. They're ending the test on a vocab question. You need to know what a transmutation is. A transmutation is when the change of one element into another. Now, that's exactly what it is. So that means that that's what we could write. The reaction changes one element into another element. Uranium into thorium element. E-M-E-N-T and period. And at that point, that's it. So we're going to pick up the mic. We're going to drop the mic, and we are absolutely done. Congratulations on getting 100 on this Regents, and good luck on the Regents that you take.